just see what happens. It does work. All right. Okay. I believe we're live on YouTube now. I feel like I've been sick for so long. I've like forgotten how to do everything. I've forgotten how to stream. I've forgotten how to talk. I've forgotten how to be a normal person. Okay. Is there anything else I need to do? Oh yeah, Blue Sky has like a thing where you can appear as live. Forget where that was though. Go live. Oh yeah, there we go. Let me just do that. Okay. I have no clue how far I'll get into this. We'll see what happens. I am super unfamiliar with a lot of differential geometry. I've been looking through Keen and Crane's course on it, and there's a lot of stuff that I'm kind of missing in terms of whatever you would learn if you go to college, I presume. And so I've been I've been mostly learning math on a need to know basis, you know? Because I never studied like anything like beyond high school math. And so all of my math knowledge is very like patchwork from whatever I've happened to need in my projects. So when I was looking through this this lecture series on discrete differential geometry, it is very dense on stuff that feels very domain specific. So like I still barely know what differentials are and what K-forms are. That's where I'm at. I have a hard time, like, I don't know. You have to like separate all the different concepts between like derivatives versus differentials versus the like vector derivative and oh boy. But it is interesting. It is really fascinating how like a lot of the stuff in differential geometry connects to geometric algebra, which is kind of funny. Let me actually prepare my sketch. Not my sketch, my sketchboard. I'm about to draw a sketch. New. Large, please. A lot of D's and delta, that means slightly different things. Yes. Yeah. Exactly. Where's my tablet pen? Oh wait, there it is. And the funny thing is, like, because this is specifically discrete differential geometry that I'm learning, like the combination of learning differential forms in a continuous setting, but then applying it to a discrete setting means that not only am I going to use the like symbols for differentials and all the continuous stuff, but I'm also going to use the symbols for the discrete stuff, and I'm also going to be using the symbols for the gradient and the Laplacian. And these are a lot of symbols that are all intermixed and ambiguous, and so you need to be like super careful about what means what. It's a lot. And so honestly, a lot of this is going to be just me trying to remember everything and just rehearsing it and asking whoever in chat knows this for what I'm missing, because I will be missing some stuff. Twitch has said it's okay to merge chat. Knowing Twitch, they will punish whenever they want, though. I have only seen stuff about how you're not allowed to interleave chat messages in a single feed, but you're allowed to have them separate. That's how I've understood it. So if that's changed recently, that would be nice, because it would be nice to have to combine them. Is there a fundamental theorem of differential geometry? I mean, if you're asking about the fundamental theorem of calculus, then a lot of that stuff carries over to the differential case. But there's also a lot of things that kind of diverge in the discrete case. Sorry, I meant discrete. I said differential. So let me just switch scenes. Good luck with the learning. Thank you. I always thought you had formal math training. No, not beyond high school. Does differential geometry involve differential calculus? Yes. I believe so. Okay, have I closed all the tabs that I want to close? These should go here. This should go here. There's some stuff in. There are some fundamental theorems that are the fundamental theorem of curves, but I think that's about. I think it's a 2D curve is fully defined by the curvature. I think that's the fundamental theorem of curves. 2D curves? I forget what it's called. And then for 3D, it would be the equivalent, but including torsion and not just curvature. I think those were the ones I've heard as the fundamental theorem of curves. Okay. Oh boy, I'm gonna have to take a lot of notes during this. I'm just gonna open up a separate notes thing. Okay. So what I'm gonna be, my goal with this is to learn enough so that I can implement a parallel geodesic distance function effectively for a 3D mesh, or what in the math lingo I think it would be called a simplicial complex, but that's just a 3D mesh in game dev terms. Okay, all right. Let me I need to arrange my stuff. There we go. And then OBS. I went live on YouTube way too early. I'm sorry. I usually go live on YouTube whenever I'm ready to just hit the ground running, but is there a book you're reading to study DF? I don't know what DF is. Differential functions? Differential geometry. No, primarily I am looking through Keen and Crane's series on discrete differential geometry. It's on YouTube. It's a very good series. I highly recommend it. So I watched that through once, and I did not absorb all of that information. Okay, all right. Let's see if we can switch scenes. Oh wait, do I need these? No, that's okay. All right. Okay. Wow, we have a scene. My voice might give out after a while. Hopefully it won't, but ever since I was sick, my throat has been kind of painful. And any day that I talk, the next day my throat is sensitive and I struggle to like make certain sounds. It's hard to talk to my cats sometimes. So hopefully I'm not going to over like strain my voice or anything. Lots of tea is hopefully the solution. Okay. So my actual use case. Let's start with my actual use case. So as some of you know, I am working on a 3D modeling tool. So I'm gonna just open that up real quick. So I'm working on a 3D modeling tool, and obviously in 3D modeling, there's a lot of operations you want to do on meshes. And there's one specific operation where if you select some object, you want to move other objects around it with kind of like a soft fall off, right? And so that is something where what I'm going to study today would be useful. So like if I select this face, for example, if I have soft selection enabled, I would want it to not just move this face, but it should also slightly move the surrounding faces, given some input radius for how large that influence should be. So by moving this, the end result would not be like this jagged thing, but like these would also move out slightly. I don't have camera-based movement implemented yet, so it's not going to be perfect. But yeah, you would basically have this kind of fall off where you kind of have this soft bump fall off type of thing, which I don't have. This was horribly explained. I should just draw this. Yeah, so if you imagine a mesh with a bunch of vertices, if you grab this vertex and move it up here, then generally you would get this kind of shape. It would just pull that one vertex, right? But maybe you want to have a thing where even if you only have this vertex selected, there would be some kind of influence curve, kind of like a bell curve, where these vertices would also move to some extent. So you kind of get this soft selection type of thing going. So this is a very common thing in 3D modeling tools, to have a soft selection tool. And yeah, so what I'm going to be doing is the problem that I need to solve is what is the distance from your selection, which, you know what, I should color code it. Your selection is blue. Like, what is the distance from your selection to every other vertex in the mesh? What happened to my... Oh. Like, what's the distance from this vertex to this vertex? I need to know that in order to have a fall off, because the fall off has to happen in some space, right? And there's kind of two different ways of approaching this. So, for example, let's say you have some mesh. Let's just draw a very simple mesh like this. You know what? We're gonna add one more face, just because. All right, so let's say that you select this vertex. So if you select this vertex and you have soft selection on, then it needs to influence neighboring vertices by some amount. And in order to know how much it should be influenced, we need to know the distance to every other vertex, right? So we would need some kind of way to measure the distance from this vertex to this vertex, right? We need to know that distance. We need to know this distance. We need to know this distance, and that distance, and that distance, and that distance, and that distance, right? So the lines that I'm drawing right now are representing the Euclidean distance. So Euclidean distance is kind of you can just replace Euclidean with the standard distance. Like if you think of a distance between two vertices, you usually think of the Euclidean distance. So whatever the length is of these red vectors, that would be the distance to each of these vertices. But that is not always the type of soft selection that you want. I do want to add support for this, but adding support for this is actually pretty easy, so that's not a problem. So that's not an interesting problem. The type of distance that I want to implement is known as a geodesic distance. And geodesic distance is distance along the surface. So if I want to get the distance to this vertex, I want this distance all the way along here. That should be the distance to this vertex. And you'd think you can kind of do something simple, like, oh, what if you like triangulate your mesh? If it's fully triangulated, maybe you can just check distances like along edges and whatnot, right? But the problem is that geodesic distance is not always trivial, and it's not always along boundaries of triangles. So if I want to get the distance to this vertex right here, the distance would be, the shortest path would be like probably going through here to here and then to here. So like the length of this green path is the geodesic distance from this point to this point. So adding support for this, or checking for this and calculating this, is a lot more complicated than doing Euclidean distance. Yeah. And another complicating factor is that I don't just want to get the geodesic distance to a single point, but I want to get the geodesic distance to multiple points. So if I've selected these 3 points, I want to basically get the geodesic distance to from every point to whichever one of these is the closest. So kind of the minimum geodesic distance to all of the things that you have in your selection. And this is going to be a lot of calculations. Like it's a non-trivial amount of calculations if your mesh has thousands of vertices, right? And so that's what I want to, that's what I'm going to research. Or not research. Research is the wrong word. Study. Yeah. Okay. Some people have been asking if this is similar to pathfinding, and yes, it is very similar to pathfinding, because it is kind of like a distance function, but you have some constraints about the space you're allowed to navigate to. So it is very similar to pathfinding. The reason you can't really use standard pathfinding algorithms for this, the reason I can't use standard pathfinding algorithms is that it's going to be too slow. There's too many vertices and there's too many things to check a path for. And so I want to use a method for this that is heavily parallelizable, which is going to make it significantly faster, because in the end, I'm going to want to implement this on the GPU, so it's going to be a compute shader. And if I can parallelize this, it's going to be basically real time for my use cases, which is nice. I want my software to be fast and snappy, and so that's the goal. So trying to figure out if I should explain the heat method. See if I can explain the heat method without looking at the paper. That would be a good test, I think, to see if I've remembered it correctly. Let me just see what you've all written. Because sorry, I've just been yapping. You can use a kind of Dijkstra's algorithm, yes, but it's going to be too slow. Or you know what? I don't actually know if it's going to be too slow. If I did a Dijkstra's algorithm, maybe if I do that parallel on the CPU, maybe it's going to be fast enough. But that's also less fun. I want to do the fun implementation, so we're going to do the fun one. That's also a lot more complicated. So geodesic distance is the shortest distance among the edges. Shortest distance along the surface. So not necessarily edges, but it could be along an edge depending on which vertex it is. So the geodesic distance between let's call this A and let's call this B. The geodesic distance from A to B does go along edges. But the geodesic distance from A to C does not go along edges, right? So this one cuts across faces. So this one I can obviously not approximate that one with just going through the edges. Well, actually, I could approximate it, but I'm not going to get the exact geodesic distance. Okay. What you want to do is apply a Laplacian smoothing to the displacement, just need a Laplacian matrix. Yes, I've gathered it's something along those lines, but I don't know what a Laplacian matrix is, so I would need to look that up. So, I remember hearing about that in the lectures, though, so it's gonna come up for sure. Is it geodesic or geodesic? I've only ever heard geodesic, but I don't know what's common. I wonder if projecting the Euclidean distance down onto the surface somehow would give the right result. No, it would not. You might be able to use that as some kind of hint or starting point, but it's not something you can use in general, no. Because the geodesic distance can get really complicated, right? Like if you imagine some kind of S shape like this, like then you want to check you select this one and you want to know the geodesic distance to this point right here. Like this is this would not even be close to the Euclidean vector between these 2 points, right? Like this vector right here is super not representative at all, right? Because then, the actual distance that we want is going to be the distance like it's hugging this edge and then a straight line tangent to this inner corner here, hugging this edge and going all the way there. This is the distance that we want. The length of this green path is the geodesic distance. And the yellow line would be the Euclidean distance. What? Switch tools? Oh my god. No. No. Oh my god, it's over. Ran out of space. Euclidean. First what comes to my mind is to create a plane which includes the two vertices and cut this shape with this plane and then measure the cut between the 2 points. That sounds way too expensive. That sounds like it's going to involve like doing bounds testing to see if those cuts are inside or outside certain geometry. The actual solution that I'm going to be studying here is called the heat method, and okay, so here's the rough idea of how this is going to work. I have no clue if I'm going to get this right. Or no, I have some clue that I'm going to get this right. I should be getting this right. Because I watched a couple videos on this now. So I think I remember. I remember the high level stuff, but I don't know the low level stuff yet. So that's the stuff that I'm going to have to look at. So here's the general approach. Assume this is kind of like a tessellated plane. Assume there's like vertices all across this thing. The heat method has a few steps involved. So the first thing is that you have some kind of seed. So in my case, the seed would be the selected vertices, right? So let's say I have some selected vertex here. The first step is to diffuse this. So have some kind of diffusion process for taking, some point that I've selected here and just kind of diffusing it. So if you're thinking about like temperature has a very simple function where like if you assume this is a really hot point and this is like a sheet metal or something, and you want to have a function that describes the temperature across this whole plate. If you keep averaging neighbors, so let's say this is a pixel, and you have a pixel here, you have a pixel here, and so forth, right? You can kind of run this iterative function where you take neighboring pixels and you average those two. And then you keep doing this average. So this one is going to be like a little half strong there, and then you have another one that's going to be the average of these two. It's not going to be as visible or as hot. So if you keep doing this, you're kind of going to get this function that represents kind of decreasing temperature, like emanating from this one point, right? So you're going to get kind of this wavefront of temperature, or temperature change rather. And what you're going to see is basically that like the heat is going to be, 1 at this source point, and then it's going to decrease along a geodesic. So the core idea is to basically do, or this is like this is step one. Step one is to diffuse your seed, which is going to be the selection. Once you've diffused the seed, you're going to have a value that's decreasing sort of along the geodesic. I think if I remember correctly, that's not a geodesic. It is a, yes, well, yes, it's not a geodesic, but it's in the direction of the geodesic, but it's not like linear in terms of the geodesic distance, right? So then, let me just erase all of this. You know what? No, I'm not going to erase that. Okay, so this is step one. This is the is it called diffusion? I think it's called diffusion. And then once you've done that, you then have a scalar value that goes from, I guess it's 1 here, and then it goes to 0 or some lower value somewhere else. Once you have that, if you take the gradient, I believe, I think so. If you take the gradient of that, which, I don't know, the gradient of the function, I don't know what the function is called right now. And I think this is the gradient, if I remember correctly. This is the, is this a gradient? This is the Laplacian, right? Or no, wait, the gradient is the, shit, I forgot. Which one is the one where you apply the gradient twice? I feel like I'm missing one of the three. Or sometimes it's like nabla dot f. I forget which one is which of these two, but I'm pretty sure this is usually the Laplacian. Personally, I prefer to write the Laplacian as nabla squared. Oh, is this the Laplacian? Oh, maybe this is the Laplacian. Divergence. That's what I was looking for. Thank you. Yeah, this is the divergence. Yeah, divergence, gradient, Laplacian, I think, right? And then in the lecture that I was watching, nabla squared was the Hessian, not the Laplacian or Laplacian. Gradients is nabla, Laplacian is nabla squared. I thought nabla squared was, or no, wait, never mind. Don't listen to me. Just don't listen to me. It's called studying because I don't know these things, okay? Okay, I should actually just write this down. Just to make sure I got it. Okay, so nabla is just a gradient, right? And but then what was it was divergence, right? Like nabla, yeah, nabla dot f I think was divergence. And then in the notation that I'm using, because I want to match the notation of the lectures, then delta would just be the Laplacian. And then I need to add nabla squared. That's the Hessian, which is not really related to this yet, but someone is going to bring it up at least one more time, so then I can just like go to this and point at it. So that's the plan. I think this is the terminology that, or the syntax. Laplacian equals divergence of the gradient. Oh yeah. Wait, was that true? Is that true? I think actually I recognize that. But is that always true? Because I remember that was the case, but I'm not entirely sure. Because like some of the definitions for the gradient and the divergence changes for when you're doing math on a surface. Oh god, this was the stuff that was like super esoteric to me. There was something about how when you have a function over a surface, you have the concept of a Riemannian metric, which is an inner product that is not always the same as the dot product. If I remember correctly. And in this configuration, the meaning of gradient, divergence, and Laplacian changes a little bit in ways that I don't remember exactly what it was. But we'll probably get there. Okay. Yes, Laplacian is the divergence of the gradient. Okay, I should probably just... Let's just add that. Why not? This beautiful mix of symbols. So it would be the divergence of the gradient. Like this, right? Okay. Thank you for the read, Sorcery Story. Okay. So, when we do this diffusion step, what we're going to end up with is a... Let me just draw... There we go. We're going to end up with some kind of scalar field. So it's gonna be like hot in terms of the temperature analogy at this place here, and then it's gonna kind of dissipate over the shape of the mesh. So the brightness here effectively is visualizing the value that we're gonna then associate with each vertex for a temperature that's kind of dissipating over the whole thing. And from what I've gathered, the let me also switch colors on that, because I feel like I don't know, just to make these lines a little bit more less distracting. Okay, so first we're going to diffuse it. This is a relatively simple process. Average a bunch of values. It's a Not Poisson's equation. Who did the other one? Is it just Laplace's? No. Whichever one is the simpler version of the Poisson equation. I forget what it's called. Poisson equation that's equal to 0. That's the diffusion step. We're just gonna basically average out everywhere, and we're gonna get this ramp. Okay, and then is it just the Laplace equation? Okay. Okay, so as far as I gather, one of the kind of the key step of the heap method is that if you then take the gradient of this function, which I believe is just nabla. So if you take the gradient of this function, you're going to get a bunch of vectors that are pointing in some direction. I guess if this is 1, would it point towards the source? I forget. I think it points towards the source, which is kind of unintuitive, but I think it does. I seem to remember gradient points towards the slope of steepest descent, I think, is the gradient. Right? So we're going to get a vector field where we got all of these arrows pointing towards our quote-unquote heat source, or in my case, it's going to be towards the selection. Oh, crucially as well, all of these are going to get shorter and shorter because the gradient is smaller and smaller and smaller. But one of the key steps is that this is then going to be normalized. So this vector field is a normalized vector field. So all of these are going to be of unit length. And apparently, as far as I remember, all of these vectors point along the geodesic. So once you've gotten to this point, the last step is to what? Let's see. Step 3. The last step is to then take this whole normalized vector field and I believe you're supposed to somehow integrate it. Just integrate it from your selection to each vertex, you know? And something, 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 you get an answer that is the geodesic. That's the high-level overview of the heat method for calculating the geodesic. And so that's not gonna be just any kind of fall-off, but specifically a linear fall-off, so that it actually represents the distance. Yeah. The diffusion decays exponentially with distance. Yeah. So once you get the gradient of the exponential fall off, you then take that vector field, the gradient, and you normalize all of those. And so then you can somehow integrate this in order to get the geodesic distance. Yeah. That's it. There's not much more to it, but this is very much a draw the rest of the owl kind of situation. Because I don't know how to draw the rest of the owl. Especially because I'll also be doing this in a game engine, so I don't have like a Python library with a solver where I just shove in a math problem and it gives me the results. So it's gonna take a bunch of extra work because I'm gonna have to write a solver. Yeah. Why does this not sound faster than Dijkstra, considering you can just limit your vertices based on Euclidean distance? Well, Dijkstra has well, there's a bunch of problems with Dijkstra, right? Because my source might not be just a single vertex. My source can be multiple vertices. So I could have a mesh with 1,000 vertices, and I've selected 500 of them. And I don't want to do like a Dijkstra from every single selected vertex. That's going to be super expensive. And another problem with Dijkstra is that you're kind of, you know, you have kind of a network of vertices, right? And let's see. So like if you're going to do like a Dijkstra type of thing, you need to like start from a vertex and then you step out one level to the next boundary. And then you kind of need to keep track of this front of distance checking to every single thing. And the problem with this is that it's not very parallelizable. Like I need to do the inner one before I can do the outer one and so forth. So it's not parallelizable to run it on the GPU in a way that would be it's not going to be efficient enough to use Dijkstra's. Does Dijkstra compute geodesic distance? I mean, you can implement a geodesic versions of Dijkstra's algorithm for sure. It's just that it's going to be very brute force. It's probably going to be like O of n in time complexity. But with the heat method, I think sorry, wait, did I say O of n? Maybe I meant O of n squared. I forget. The thing that's nice about the heat method, well, there's many nice things, is that the diffusion and the integration, as far as I've understood, these basically boil down to solving a linear system, which I've gathered is a very common thing to do in math. But I have done this like 2 times in my entire career as a game developer. So solving a linear system is still something that's relatively unknown to me. So I always forget which part is the answer that I want and which part is my input. And oh god, I don't know. It's just not a very common tool for me, at least, in the stuff that I've done. Yeah, I've implemented a solver once. I think it was it LU decomposition? I forget. Yes, I know that there's a lot of reference implementations. I can just grab code from somewhere or go ask some AI, but I don't want to do that. I actually want to learn how to do this. Okay. Why do we need the heat method in game development? You're usually you're not gonna need this in game development. Maybe in some engine development, or if you're doing like physics simulations and whatnot, but this is very rarely something you need. So in my case, I need it for my 3D modeling tool because I'm making a 3D editor. And I need it for soft selection. So if I select a bunch of vertices and I move these, I want to have a smooth fall off so that I don't have this sharp edge from the things that I moved. I want it to have this like curved, soft pulling out of these vertices. So yeah, this is where I'm actually going to be implementing it in practice in this modeling tool. I think I'm also going to be doing soft selection for faces. And I don't know if this is true, but it feels like I should be able to just use the vertices of these faces and use the same method. I don't actually know if, like, do I need to get the distance to the edges here, or can I just use the vertices? It feels like the vertices should be very close. There might be some edge cases for this, but I don't know. Wouldn't it be better to use virtual textures for something like that? Virtual textures, I think, is entirely unrelated to this, no? I'm not sure, or like, how would you use the virtual textures for this? I'm not sure how you would implement it. That sounds way too overkill for dragging vertices. Well, it's for soft selection, not just dragging individual vertices. So the soft selection part is the difficult part, not the moving vertices. Moving vertices, I can already do. Yeah, okay. Trying to figure out where do we start for all of this. I think I should. I think there's two things I should do. One, I need to write down the steps, and then kind of just suss out, like, what are my questions? What are the unknowns? What is it that I'm not sure about? And then eventually try to answer each of those questions. And then two, ahead of implementing all of this, I need to be able to visualize data on the mesh. So I'm gonna need to have some kind of visualization in the 3D editor, unless I do like a separate implementation. But it would be nice to just do it in the viewport, because because I'm basically gonna need that down the line anyway. I want the users to also have visualization on top of the mesh, so I'm gonna need it regardless. So if we're just doing soft selection, the gradient and integral might not be necessary. I wonder if diffusion would be sufficient to get a set of weights. The problem with only doing diffusion is that it's not going to be linear. So if I want to have something where I can configure the radius of my soft selection, then that radius doesn't have a distance value to use as a reference, right? So I will need some kind of linear distance. All right. Okay. Geodesic distance. Wow. These are all of my notes so far. I hope you appreciate all the information I've written here. Okay, so so the first step is to diffuse. No, you know what? Let's use these numbers. 1, 2. This would be, I don't even know what to call this one. This is like a I get the gradient is a normalized gradient. This is a trivial step, and then this is the. Did someone say that this was called a line integral? Is it called line? What's the difference between a line integral and an integral? Okay, all right. So this is the paper for the whole procedure. There's also a video. Actually, I think I'm gonna go. There's a slightly different version that's using the vector heat method. But I think this video is a better quality. So, and they did talk about. Yeah, this one is a little bit more complicated because you need to be careful about parallel transport. Okay. Maybe I should just use the look at the original heat method. The vector one is going to complicate things. Let's not do the vector one. 12 years ago. Good lord.
It's a single process.
This one is like 480p. It makes me feel sad. Everything looks so smudgy. All right. Okay. Oh, someone asked if I could just like sort of just treat the distance or treat the diffused version as the distance itself. Using this thing called Vardon's formula. It's honestly kind of a cool idea. It's basically if you have a normal distribution of something, if you apply Vardon's formula, you basically get the linear version of that, which is a really neat trick to kind of just transform a Gaussian into a linear function. But it generally doesn't work well enough. Like there's too many inaccuracies if you have a slightly like bumpy, bumpy shapes, right? And yes, this is gonna stay on YouTube. So yeah, this is where like because we can't make use of Vardon's formula, there's instead 2 extra steps, which is going to be normalizing this gradient and then doing a Poisson's equation solve in order to get the distance, which is the integral. Yeah. And that's the thing that I'm not entirely sure how to do. Crane mostly deals with triangulated surfaces, and ideally there should be Delaunay. I think he talked about it at the end of this video, where as long as your topology is mostly well behaved, it's accurate enough for my use case, is what I gathered. Like I could do stuff like, I don't know, there's a whole extra process you can do where you have an intrinsic triangulation of the mesh. And then using the intrinsic triangulation, you can tessellate it further, make sure that that fits the Delaunay criteria, and then you can do the distance functions on the intrinsic Delaunay mesh, which would be a lot more accurate. But I don't think I need that accuracy, and that is also significantly more complicated because I need to add so many more data structures to that. So I'm at least going to try without all of that extra work, just on the geometry itself. So. Okay. So let's see. What is the first step? Heat equation. Okay. That is just diffusion. I don't even know how to do that properly. Like I know how to do it naively. I don't know if he talks about the discrete. I think he does here somewhere. Or no. Maybe he doesn't. He does not? Okay, I did see a video where he did talk about
distance
it. But you know what? Maybe we can look at the paper. So complex for a small application, probably not worth it. Did you just call my application small? That seems like an insult. I don't like that. Okay, related work is iconal equation. I feel like some equations just look so trivial. Like the like iconal equation. It's just like thing is unit length. It's like I don't know. It just looks weird when it looks too simple and you're like, am I supposed to gather something really cool from this? And it's like, yeah, I guess you could because this is like the change across the surface, so it's more interesting because of that. But it just looks so funny when you have these like formulas that just look too basic for what they're supposed to describe. Poisson's equation is like it's the same thing for that one, I feel like. Okay. Yeah, these are the steps. Look, we got it. These are the steps. This is the heat function. We have the selection in the middle. We diffuse that quote unquote heat or that selection across the surface. Then we get the gradient where you get arrows pointing up from colder areas to warmer areas. And then you normalize and I guess flip those vectors. And then you do the linear system solve. Yeah. Okay. Integrate the heat flow for some fixed time t. Why is it called integrate the heat flow? Oh yeah, because heat is a it's like a differential equation, right? You have a you're setting up like the rate of change of temperature should be some value. That's the heat flow. And then when you integrate that, you get the heat. Right? I think. So is U heat in that case? Or is U dot oh my god, I feel so stupid. This was a mistake. I'm gonna be bad at math in front of people. Why would I go live being bad at math? You know? So we're trying to find distances along an arbitrary shaped surface here. Kind of, yes. It's specifically a it's specifically for 3D meshes. So it's a special case. It's not a general solution, and it's not even a continuous solution. So I feel like there's kind of two different approaches I can take to this. Either I try to make sure I understand every single step, even in the continuous expressions, or I jump directly to the discrete variants, which I believe he talks about here. But if I jump to the discrete versions, I'm not going to have a very good understanding of it, I think. Yeah, these are the discrete. Yeah, this is the discretization of the whole thing. I feel like I do want to understand the continuous stuff. I need to make sure that I do that. I think that's why I'm doing this. That's why I'm not just copy pasting a solution. So you know what? I need to understand this. That's just the way it is. Okay. Integrate the heat flow. So does that mean that my selection is my selection basically going to be a statement of this is the temperature increase at my selected set of vertices. And then I have some boundary condition. And then I guess I'm a little bit confused as for why the heat flow, because here it sounds like the seed of the whole function, it sounds like that's a it sounds like that's not the state, but rather the rate of change, which is a little confusing to me. You're still using iteration methods for the round corner bevels? Yes, I kind of left it there, so I haven't touched that code for a long time. The heat equation is a partial differential. You know what? I should just search for the heat equation. Okay. Oh boy. Okay. Given an open subset U of Rn. This is so formal. Okay. Where's the Cartesian coordinate system? Oh my god, thank god. The math people are way too obsessed with coordinate-free expressions. It makes my head hurt. Okay. So, if we have the specific case of a function of xyz coordinates and time, u is a solution of the heat equation if okay, so partial u, partial t, so the change of is u heat? I guess that's the thing I'm not entirely sure about. Just u. And then partial u is the heat flow. Or partial u, partial t is heat flow. Is that it? Oh, wait. Okay, so... Oh yeah, the dot is Newton's notation. I completely forgot about that. Right. Right. Okay. 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 You only need a short time diffusion? That's what makes it simpler? Yeah. One question that I have right now. Okay, so here's something that I'm wondering. Like, I'm gonna have a pretty dense mesh. Let's just assume it is absolutely ultra dense. Oh my god, I hate Photoshop's shift line stuff. You know what? I'm not even gonna draw straight lines. Photoshop is too annoying at letting me do that with a tablet pen. Okay, so in my mind, if I'm running the algorithm for the diffusion, if I wanted to do like, let's say I didn't read anything anywhere about this and I just had to try to do it in a naive way, I guess I would probably do some kind of like, you know, for every face connected to a vertex, do some kind of averaging to get values for the adjacent vertices, right? So I would get some kind of new value for all of the neighboring points. But then I don't have data for this point. Like, do I need to run like an iterative function like n times where n is like the longest graph distance or something? Because that feels kind of wasteful. Maybe it's not too bad, but... Or maybe it's just because I'm like trying to think of how to do this on the GPU and I'm like parallel brained. And maybe this would just be a better thing to do on the GPU, or the CPU. You could do this in a single step using the greens function. I don't know what greens function is. I recognize that. I'm not sure how I would apply this. Like it just feels like I'm gonna have to do n steps, where n is the like maximum distance away to until I cover the entire mesh, right? But maybe I'm guessing too much. I should just read the paper. Okay. Okay. Should I read from the start? Or should I cheat? Yeah, I'm just gonna read it. Just need to get a little bit more comfortable and get my tea ready. And sit. I just want to sit different. What's the paper called? I can send you a link. There you go. Okay, all right. Is it possible to solve a linear equation on the GPU? It will be. That's the idea. I'm probably gonna have to implement it myself, but yes. But I've gotten the impression that stuff like LU decomposition would probably be good for this, maybe? Maybe there's like better, like parallel linear system solving methods out there. But I vaguely recall that LU decomposition was good for that, but I might be wrong. That's the only one I've looked into. Okay. Geodesics in heat. See, it's a funny joke because like cats are in heat, I guess. Maybe, I don't know. I don't know if they even made a pun about that. Okay, a new approach to computing distance based on heat flow. All right. We introduced the heat method for computing the geodesic distance to a specified subset, in other words, point or curve of a given domain. I assume multiple points is going to be a valid subset. As far as I understand, there's none of the equations I've seen so far, and what I remember, would present a problem if I don't have a point or a curve. It's going to work if I have multiple points as well, I think. If I remember correctly. We'll see. The heat method is a robust, efficient, and simple to implement since it's based on solving a pair of standard linear elliptic problems. Linear elliptic problems. Oh boy. Okay. Do I need to know what linear elliptic problems are? I do not. Okay. It feels like I don't need to know exactly the nuance of that, so. Simple to implement since it's based on solving a pair of standard linear elliptic problems. It's just a category. I don't need to know the nuance of the category, I think. The resulting systems can be prefactored once and subsequently solved in near linear time. Linear is actually really good. I didn't know that it was linear. I thought it was like, well, at least better than n squared, but okay. In practice, distance is updated an order of magnitude faster than with state-of-the-art methods while maintaining a comparable level of accuracy. The method requires only standard differential operators and can hence be applied on a wide variety of domains, grids, triangle meshes, point clouds, etc. We provide numerical evidence that the method converges to the exact distance in the time limit of refinement. Oh wait, in the limit of refinement. Oh, just like, yeah, it converges. Or actually, what does limit of refinement mean as opposed to just converging? I never heard that terminology before. We also explore smooth approximations of distance suitable for applications where greater regularity is required. Okay. Oh, in the limit of refinement, I'm guessing that means there's some inherent error if you don't refine your mesh data. And so it's going to be the exact distance is still kind of capped based on the refinement you've done on the mesh, I think. Right? Okay. Right. We provide numerical evidence that the method converges to the exact distance in the limit of refinement. We also explore smoothed approximations of distance, suitable for applications where greater regularity is required. Okay, I presume regularity in this case just means the English word regular and not the math term regular. I guess maybe it's both, actually. But I'm guessing it's just like there's irregularity if there's imprecision. And you don't generally want that. Limit of refinement means performing the algorithm again wouldn't improve accuracy of the output. Right, yes. That makes sense. And then the refinement refers to the mesh refinement you could potentially do. Okay. Okay. Categories and subject descriptors. I-35, computer graphics, computational geometry, and object modeling. Oh, are there like universal categories for papers? And these are like the, I don't know, ISO standard of categories that are like probably like 40 years out of date. Is that the... I remember I had to, when I had like, when I was shipping some small like 3D printed toys, for like the EU regulation for shipping and everything, I had to pick a category for what my little toys were. And there were like a gazillion different categories, like kind of structured in a similar way. That was just like whatever the European Union has decided are the complete like categorization of everything someone might want to sell. It was kind of funny looking through those categories. It's sort of the same when you do your taxes. You have to pick like a category for the type of work you do. You also have these codes. I know it's always kind of funny looking through those because you always find like some like really archaic job that people just don't do anymore. It's kind of funny. I don't know if that's the case for papers though, but regularity refers that if you want smoother level sets of distance, you can control that. Avoid cusps. Yeah. I just feel like the definition for regular that I've heard is in terms of a function where the derivative is never zero. That's a regular function, I think. But in English, regular has a more like colloquial and less precise definition. But it actually lines up here. Like it sort of means the same thing. Like you don't want to have cusps because cusps introduce a bunch of like jaggedness, and we don't want jaggedness and misbehaving algorithms. So anyway, all right, keywords, reference format, blah blah blah. I clicked the reference format. It took me to some location. Spoilers. Oh my god. No spoilers. Okay. Imagine touching a scorching hot needle to a single point on a surface. That's the temperature, the heat equation. Over time, heat spreads out over the rest of the domain and can be described by a function. Oh, okay, k sub t and x of y, called the heat kernel, which measures the heat transferred from a source x to a destination y after time t. Oh, okay. Sure. One thing that throws me off so much about reading math from like people who actually do math professionally, is that they use x and y as just like that's just variables. We just toss them around. X is a variable name, y is a variable name. But I'm so used to working in coordinates that I'm like, oh wait, x, that's like that's a coordinate along a spatial dimension, and y is also a coordinate along a spatial dimension. But like x and y is tossed around a lot. I don't like it. I have to reconfigure my brain every time I read a math paper. Okay, all right. This is a weird syntax, but okay. So let's just write that down to make sure that we are following along. So we've got k sub, okay, t x of y. I'm not entirely sure if y is the manifold or if y is a specific point on the manifold. I'm assuming it's going to be a point. Okay, so this would be the heat kernel, where we've got, well, we've got time. And that one I'm going to put there. And then what would x be here? So x was the source. And y was the destination. I guess x would be the heat source. And then destination would be the place you want to measure at, right? This equation is too short to live centered like this. So you know what? You're also going to be in line. Kerbal. You know what? I just don't know how to use a keyboard. Wait, what? Jesus, the amount of front loading you do, and yet your kind programmers can read more novels than most other kinds. Why the double standards? I have no idea what you're talking about. It feels like you're attacking someone. Am I getting attacked? Why would you do that? That would be like a pretty bad thing to do. Okay, heat transfer from a source to a destination over time t. Cool. A well-known relationship between heat and distance is Verdon's formula, which says that the geodesic distance between phi, is that phi? The geodesic distance phi between any pair of points x and y on a Riemannian manifold can be recovered via simple pointwise transformation of the heat kernel. Okay. All right. I have a few questions, but let me just write this down first. So what was it? It was phi. Okay, phi is the geodesic distance, the function of the geodesic distance between 2 points x and y. Okay. So that is equal to limit to 0. Square root of negative 4. What? For t log. Okay, spicy. We're doing log. Wait, what? Oh. Oh yeah, because it's in the square root. I accidentally deleted a thing. Okay, and then that's K, that's the heat kernel right there. Okay. Valid. Okay, this is Varadon's formula, I believe. Which says that the geodesic distance phi between any pair of points. Okay, so let me just take this. This is the geodesic distance between 2 points. Can be recovered via simple pointwise transformation of the heat kernel. Right, so as the time step approaches 0 of this transformation of the heat function, we get the geodesic distance. Okay. This is in some sense just kind of like taking the is it like inverting the Gaussian to recover the linear variable? It's unintuitive to me though why the time step or how that would play into it. But maybe it doesn't have to be intuitive. Okay, readers. Hello, readers. Welcome to reading a paper. So this recovers the notion of distance from how heat dissipates. Yeah, exactly. I think this is like the Gaussian to absolute value. Yeah, linearizing the Gaussian. But I just don't fully understand how how you would get the, because it's not just inverting the Gaussian, right? There's also something about the time step here approaching 0, which but yeah, anyway, I probably don't need to know how to derive this relationship. I think it is okay that I don't understand that, but all right, okay. Riemannian manifold. Okay. Manifold is a it's just a thing, right? It's a thing where you have some notion of space along the thing. Riemannian manifold, I've forgotten what that is. What's the, do I need to know the Riemannian part here? A shape of lower dimension. So it's like a 2D surface in 3D space. Does that count as a Riemannian manifold? Because I'm guessing 2D surface in 3D space is my actual use case. A mesh, yeah. A simplicial complex in Keen and Crane's terminology. A Riemannian manifold has a defined metric on it, so inner product is available. Right. Right. That's the Riemannian metric, right? I have a hard time imagining like what is a non-Riemannian manifold in that case? Your manifold is most likely Riemannian unless you do some funny thing with distance like relativity. Okay. Not all manifolds are augmented with a metric, but then what kind of manifold would that be? Space-time is semi-Riemannian. Oh, okay. Right. So if you like, is it like if some of the dimensions are not spatial physical things? Yeah, like space-time. Is that where things get weird? Or they become non-Riemannian, I guess. Is half-edge going to be inclusive of 4-dimensional artists? No. But I will be making use of quaternions if you consider those to be 4-dimensional, so. You can think of manifolds that are not space-like. Okay. As in, if they're not space-like, then they're usually not Riemannian. Okay. The time dimension has an opposite sign of the metric as opposed to the space dimension. Okay, I am not fully looped in on what a metric is. The only thing I remember from the stuff that I watched is like you need to define or you can define, and you usually define a symmetric product, usually called the inner product, and then you sometimes also have an anti-symmetric product, which is usually called the exterior product or the wedge product. And once you've defined those on your manifold, that makes it a Riemannian manifold. Is that sort of it? And in Euclidean space, those things are kind of trivial, where like the inner product is just the dot product. And the exterior product is usually some version of the cross product. Metric is basically the kernel of a generalized dot product. Yeah. Okay. Of course, you know this because your talk on quaternion is stellar. Thank you. I've learned that those are part of what they call a divisible algebra, or like a division algebra, and that that entire family contains only 3 items, which is a complex number, quaternion, and octonion. Yeah, it's kind of fascinating how all of those categories shake out. I think it's like when you go from like scalar values to complex numbers, you generally get more and more freedom for when you go to complex numbers. Complex numbers are so nice to work with because you usually get answers to every operation you throw at it. But then once you go higher, you start losing a bunch of properties where like, okay, when you go from a complex number to quaternions, you lose commutativity. And then when you go from quaternions to octonions, you lose, I forget what it is you lose. You lose some other property like linearity or something. And then there's another, when you go up to like sedonions, you lose another thing. And it just becomes like a nightmare to work with, like the further you go. And all of that stuff kind of affects the formulas that you would use. Because like you might have memorized a bunch of like, oh yeah, you memorized some kind of way to do differentiations. Like, oh, I have some formula and I want to differentiate this function. But if what you're differentiating is a bunch of quaternions, you need to make sure that the formula that you have for differentiating does not assume that your quaternions are commutative, right? Like you need to be really careful about using those kinds of formulas, because all of those formulas kind of change depending on what you're allowed to do, like whatever operations you're allowed to do on your types. Okay. All right. Let me just close my curtains and then I will resume. Okay. I'm happy with understanding quaternions. I don't need higher Ernians in my life. I think most people don't really need any of these Ernians. They're pretty esoteric, but they're really cool. So you know, they're fun to look into. Okay. Where were we? We got, okay, geodesic distance, Vardon's formula. Presumably, we're not going to use Vardon's formula, I think. Okay. Right, okay, so Vardon's formula says that the geodesic distance phi between any pair of points x and y on a Riemannian manifold can be recovered via a simple pointwise transformation of the heat kernel. Pointwise, I presume, is just for every pairing of points in the heat kernel. I presume. I presume that's the only thing that pointwise means in this case. The intuition behind this behavior stems from the fact that the heat diffusion can be modeled as a large collection of hot particles taking random walks starting at x. Any particle that reaches a distant point y after a small time t has had little time to deviate from the shortest possible path. To date, however, this relationship has not been exploited by numerical algorithms that compute geodesic distance. Like I'm aware of this fact because this has been mentioned in a few other videos that I've seen. But it's not super obvious to me how that would lead to this specific formula. But I sort of get it. Sort of. Because it just seems like this is a statistical fact, but then this is an explicit formula, so I don't know. I don't know. The formula is derived from the heat equation, PDE. Okay. Is that partial differential equation? Pointwise means that the quantity can be considered for individual fixed xyt when taking the limit. Not sure I understand. Okay, anyway. Why has Vardon's formula been overlooked in this context? The main reason, perhaps, is that it requires a precise numerical reconstruction of the heat kernel, which is difficult to obtain. Applying the formula to a mere approximation of k sub tx, which is the heat kernel, applying the formula to a mere approximation of the heat kernel does not yield the correct result, as illustrated in figures 2 and 6. 2 and 6. Oh my god. 2 and 6? Hello? Where are you? 2 and 6? 2. Okay. We found it. We found 2. So, this, let's see. U sub t. So I presume this is the heat distribution after time t. So if you have a perfectly Gaussian distribution, if you apply Vardon's formula, you get a perfect linear geodesic distance. But usually you don't have a perfect Gaussian distribution. So instead, you usually have some other configuration which does not recover the linear distance magically. I think that's what that's saying. And then figure 6. Figure 6. Okay. Let's see. Left. Left is Vardon's formula. Right is the heat method. Okay. Even for very small values of t, simply applying Vardon's formula does not provide an accurate approximation of geodesic distance. Top left. Right. And that's because you obviously see that the spacing between these is a lot more dense than the spacing here. And if the distance was linear, then you would expect the same spacing everywhere, which you do see on, well, at least on this one. Wait, this one is yeah, this one is probably fine too, right? Or what's the difference between these two? Maybe it's just a difference in starting point. Does not provide an accurate approximation of geodesic distance, top left. Oh, they're different values of t. For large values of t, spacing becomes even more uneven, bottom left. Okay, so this is the t time parameter in Vardon's formula. So if you increase that, if it's a large value, you tend to get even worse results. Because the ratio between this one, the spacing here and here is awful. Normalizing the gradient results in a more accurate solution, as indicated by evenly spaced isolines, top right. Yeah, so these are the isolines. And it's also valuable when constructing a smooth distance function, bottom right. Oh, okay. Smoothed distance function. Interesting. I'm curious what smoothed with regards to what. They're probably going to cover that later. So let's go back to where we were. Okay, gonna have some more tea. We need to go deeper. Pointwise means a universal quantifier for the points come before the existential quantifier for the delta and the limit. Otherwise, it's uniform. Gotcha. Thank you. It refers to the regularization. Oh, is it? Oh, is it like the one on the bottom right has a more tessellated and well-behaved mesh, like Delani or something, but the top one does not? Is that what they're trying to communicate here? Okay, we'll see. Okay, as illustrated in figures 2 and 6. The heat method circumvents this issue by working with a broader class of inputs, namely any function whose gradient is parallel to geodesics. Yeah, that makes sense. So any function whose gradient is parallel to geodesic. So in this case, the heat kernel, heat function, heat I forget what it was called. No, it is the heat kernel. Yeah. So the heat kernel is a function whose gradient is parallel to geodesics. I think that's what this implies here. Which in and of itself is a really weird fact. I don't have a good intuition for that. It feels a little bit too good to be true in a sense. Like I sort of, my intuition says that it would be slightly off somehow for some reason somewhere, you know? I don't know. That's just a really cool fact. I don't know. It's interesting. Okay. This is called parallel transport. I mean, it's related to parallel transport, but we actually don't need parallel transport because we only need scalar values here. We don't need to transport any vectors. Luckily, if we were doing the vector heat method, then we would need parallel transport. But we're not going to need that in this case. Okay. Oh, it literally mentioned the heat method here. I'm stupid. I was just reading without actually understanding. We can then separate computation into two stages. First, find the gradient of the distance field. Is this a typo? Or no, it's probably not a typo. It's probably just, yeah, never mind. Yeah, it's just that there's a step before this of, that's what they're saying. Find the gradient of the distance field, then recover the distance. Yes, okay. So those would be, this is the gradient of the distance field that we want to find. And we find that by using the heat kernel and diffusing the heat kernel. Okay, relative to existing algorithms, the heat method offers two major advantages. First, it can be applied to virtually any type of geometric discretization. Discretization is just basically chopping it up into separate chunks, like taking a surface and we're chopping it up into a triangle mesh. Or we have a, I don't know, you have an image with a bunch of colors and then you're chopping it up into pixels. So that's a discretization in general. Including regular grids, polygonal meshes, those were literally the two examples. And even unstructured point clouds. Second, it involves only sparse linear systems, which can be prefactored once and rapidly resolved many times. So I think in my use case, prefactored once would be once per shape of the mesh, but the very reason I'm doing this is because I want to deform the mesh. So I presume it would be a very bad idea to recalculate all of these factors every frame that you pull the mesh. I presume I should just maintain the original factors, I'm guessing. It would be funny to just see what happens. It kind of, I feel like it would be some kind of either it approaches something and it kind of smooths towards some kind of solution, or it would shoot off into infinity. That's usually what you get. Prefactor refers to LU decomposition. I presume that I presume it means that the stuff that I can prefactor only depends on the shape of the geometry. So if I change the heat sources, or in my case, if I change my selection, I don't need to recalculate that initial prefactorization. That's how I interpreted this. Maybe that's not what they mean, though. Okay. Second, it involves only sparse linear systems. Okay, so I should write that down. So it's sparse linear systems and can be prefactored. If your mesh changes, you have to update the Laplacian. Right. Okay. Wouldn't you get waves in the mesh if you recompute every frame? I am not sure. I think even if I could do that, I don't think I should. I think it's kind of like if you have a... No, actually, I disagree with myself. No, I partially agree. Okay, so if I have a bunch of vertices and I make a selection and I move that selection, and if I have soft selection on, then the moment I start dragging, I compute all the data that relates to the shape of the mesh here in this state. And then whatever distance values I get when I start manipulating this, I keep those until I let go. So if I let go and then start dragging again, then I would recompute all the Laplacians and all the whatever I might be able to precompute. But there is actually a use case for recomputing every frame, and that's if you use a tablet pen. Because if you use a tablet pen, you want to be able to kind of draw terrain features, kind of like a terrain editing tool, in which case you do want it to recalculate every single frame. Which means it does need to be very fast. Anyway, I just thought it was fascinating that there's a difference between if you use like a sculpting workflow with a tablet, rather than when you drag a gizmo. Because when you drag with a gizmo, it would be weird to recalculate it, I think. Because then what could happen is that you would start stretching stuff, and then all of a sudden certain points would be able to get left behind. And so you can kind of keep dragging, but some points are going to initially move, but then stop moving because you're too far away now, like in geodesic distance. And a lot of that stuff would also be kind of frame rate dependent. So if you like yank it really quickly in like one frame, it's going to look different than if you were to just drag it slowly like this, which is kind of funny. But anyway, all right. So it involves only sparse linear systems, which can be prefactored once and rapidly resolved many times. This feature makes the heat method particularly valuable for applications such as shape matching, path planning, and level set based simulation. What is level set based? I don't think I need to know. I'm just curious what that is. If you care about the entire distance field, this method still sounds great. I do care about the entire distance field, yes. Well, sort of. I care about it, the distance to every vertex, yes. But not the distance to like points on triangles. So luckily I don't need to know that. Oh god. I guess that would be like an even more accurate version of this, where like the even more accurate version of this is to like sort of ideally consider the net effect on entire faces, and then sort of fit that to the expected shape of the given fall off that you have in the of your brush or your shape that you're using for your thing. That would probably get significantly more complicated, and it's already complicated. So anyway, all right, level set based simulation, such as free surface fluid flows. Okay, I'm not sure what free surface means. Level set base tracks the interfaces that change shape instead of tracking the interface directly. What do you mean by interface in this case? Also, thank you for the raid. Cousin makes games. Oh, updates only locally? Is that what level set base simulation means? Okay. Which require repeated distance queries on a fixed geometric domain. Moreover, because linear elliptic equations are widespread in scientific computing, the heat method can immediately take advantage of new developments in numerical linear algebra and parallelization. Parallelization, hell yeah. This is the thing I'm going to lean into. This is the thing that I don't really have in game development because I'm not in a Python environment, but that's part of the fun, you know. I'm gonna do this. It's gonna be okay. Okay, all right. We have already seen this image. Okay, why do scientific papers why are they forced to move their images to like whoever the heck knows where? It's always like, oh, check out figure like blah and blah, and then it sits somewhere completely different. Is it just like, do they have like some kind of like paper cop that will arrest you if you don't have long chunks of text? Like, are you not allowed to like separate your text with images? Is that like illegal somehow? So I feel like it's always weird how they have this like huge like spatial separation between like the text describing the figures and the figures themselves. It's really strange to me. Probably the text editor they used. Do you not have control over where your images go in LaTeX? Surely you have to have that kind of control. No way, it's just like you don't? What? In LaTeX you do? Yeah. Editors forces stuff. Editors as in like software, or editors in terms of people who review your paper? Or paper editors, right. Oh, formatting guidelines. Formatting guidelines often require images to be near top or bottom of column in LaTeX for papers. Okay. Papers are not allowed to be easy to read. All right. Because you usually reference figures multiple times throughout your article. So you're saying that they're placing the figures at the average position of all of their reference. Maybe there's like a feature to automatically do that in LaTeX editors. Like, you know what? This one should be the average of every mention. That's a differential equation, actually. Because the moment you move the image, the texts, the reference locations also change. I wonder if that converges. That's not what I'm supposed to learn. Okay, related work. The prevailing approach to distance computation is to solve the iconal equation. Okay. So this says the magnitude of the gradient of, is phi still geodesic distance? I'm guessing it is. Yeah, it should be. Solve the iconal equation. So the isn't this basically just saying that the speed, this is like arc length parameterization, but for surfaces and with respect to some geodesic distance, right? So it's like, yeah, I think. All right, subject to boundary conditions. Okay, so we have the geodesic distance, and then there's a vertical bar sub gamma equals 0. Oh, over some subset gamma of the domain. I don't understand this notation. Because because this is not saying that, no, wait, okay, I'm thinking of the wrong boundary. I'm thinking of the boundary of the mesh, but this is not the boundary of the mesh. This is the, right, this is the source. This is the heat source, but rather it just says distance should be 0 across some thing. Okay, I think this is basically just saying, yeah, okay. So I've never drawn this letter before. Phi? It kind of looks like the Danish letter. Is it pronounced like or something? Danish is super weird to me. I don't know if that's the sound, but they have a lot of those sounds in Danish. Okay, subject to boundary conditions. So when they say phi, this is a really weird notation. What's this vertical bar notation? I don't know how to write gammas. It's like a Y. Over some subset. Okay, so yeah, okay. So I think this is basically just saying that you have some piece of manifold, and then at certain locations, because this is the geodesic distance. So basically this is just saying somewhere gamma inside of the manifold, distance should be 0. I think that's all this is saying. It's like a super formal way of saying I want it to be 0 somewhere on my thing. Yeah. But it's the formal way of writing that, I guess. That the iconal equation should evaluate to 0 over some subset gamma of the domain. 0 distance somewhere. And I guess the point of the subset is that it cannot be 0 outside of the geometry. And then the top one here, this is basically just saying that the speed or the gradient of the geodesic distance should always be 1, which is a kind of arc length parameterization, but in 2D in this case. So like, if you are tracking the change of geodesic distance, it should always be of unit magnitude along the geodesic. So there's no like variation where you would have, it would like slow down in certain places and then like speed up later or whatever. You wouldn't have that kind of behavior. So this would not be allowed, which if it's a distance function, that makes sense. Okay. Is that saying that that distance is 0 somewhere on the heat source? This is not directly related to the heat method, I believe. I believe this is just making a statement about a distance function. And it's just saying that we want to have some distance function where the gradient is always of unit magnitude, and it's 0 somewhere. Actually, there is a the sign distance function. Yeah, so there is actually kind of a one-dimensional analogy here. So like, if you sort of imagine like a graph, and you imagine you have some kind of like heat source. Actually, we should be using a warm color for heat. Do we have a... That one's warm. So if you have a few like heat sources, then the distance function would look something like this, right? So then this curve here would be phi, right? And what this part is saying is basically that these need to be have a rate of change, or the magnitude of the rate of change of these should be 1. In the one-dimensional case, that means it either looks like this or it looks like this. Those are the only two options. But on a surface, it gets a little bit more complicated because you can sort of have these linear distances, but they twist around in various ways. But basically, when it says that the magnitude of the gradient of the distance function equals 1, it basically just says you're not allowed to have any other weird ass shape here. Like you're not allowed to have some part that's like a weird bump or like some kind of sharp spike like this. Like it literally has to be with a rate of change or a speed of 1. I think that's what that's all it's saying. So this is kind of like a just a one-dimensional version of that. Distance must increase 1 meter per meter. Yes. Okay. I'm so not used to all of this like this formal language. That's why this is a little bit slow. So I hope there's no like actual mathematician watching this, because then this would probably be kind of painful. Gets a little messy. An SDF is always iconal, but a solution of the iconal equation isn't necessarily an SDF. I think it depends on the type of SDF, right? There's, I think there's some. I think people usually like distinguish them between like, okay, this is a real Euclidean proper SDF, and then you have it's like there's certain SDFs that have like non-trivial solutions. So sometimes you can be okay with an SDF that's not actually iconal. If all you need is if all you need is the boundary and you don't super care about the rate of change across the field, then usually if you just need the boundary, then it doesn't matter too much. Like if you're doing like SDF tracing for like rendering the boundary of an implicit function or a signed distance field, like you don't always need like the actual Euclidean accurate distance. You can kind of you can get by with some less accurate version usually, but it really depends on what you're using it for. So if you're doing stuff like you want to expand your signed distance field, or you want to contract it, then you do usually need Euclidean distance, assuming you want to expand it along Euclidean distances. As far as I know. What is this vertical bar? I've seen it in a few places. This weird notation. What is that? Usually it's bigger. Maybe that's a different one. It's like bigger, and then there's like a thing here, sometimes a thing here. I don't usually know what that means. Or maybe it's always dependent on it. In my experience, people use math notation in very custom ways, so it just depends on what paper you're reading, so maybe it's not a universal thing. In this case, it must be restricting the domain. The one you just drew is evaluation. Okay, so is this a restriction and this is the evaluation? Is that sort of how it is? See, evaluation notation. Okay. Interesting. That's potentially useful. Because one thing that really bothers me sometimes about math notation is that you have to track ambiguities very carefully at all times. and it's kind of exhausting. Because sometimes you have like sometimes you have a bunch of math that's like, oh, you have alpha of x, and then there's another parenthesis, and there's like y wedge z, and you're like, okay, is alpha a function that accepts x as an input, or is alpha a variable that gets multiplied by this? But then, okay, but if it's the only thing inside of the parentheses, then we can assume it's a function. So it's probably a function. You have to like do this like whole song and dance. I hate it. I hate it so much. I don't like that. It is super annoying. And it's a little bit annoying, in particular, when I was watching the discrete differential geometry lectures, where you have these K-forms. I still haven't quite landed on what K-forms are. I fully get K-vectors, because that's basically just geometric algebra, bivectors, trivectors. But K-forms, I still haven't quite landed. It feels like it's like a, I don't know, it feels like it's just, what if we turn K-vectors into functions that are differentiable? But it feels a little bit vague how that happens. And the notation makes it kind of confusing, in my opinion. Math paper should just be done in lean, right? Programming for all. I used to agree with that, but I don't really agree with that anymore, because math and code are made for different purposes. I think a good example is kind of the math has a lot of like coordinate-free expressions, and it's about relationships and structures and patterns. But code is usually a lot more about a process. It's a process that has a bunch of states, and you want to reach some kind of goal, and you want to compute a bunch of things, right? But math is not always about computation. Math is quite often about, or usually about, relationships. I feel like math is usually computation when you start out as a kid. That's when it's mostly about computation. But then it becomes kind of more and more abstract, at least from what I've been able to tell. And so, but obviously, code has the advantage in that it's easier to read, and it's especially easier to read if all you care about is you want a solution, right? You want a solution to a problem, and you don't care about all the mathematical relationships. Then math just gets in the way, and I sort of get it. But fundamentally, like, you as an engineer, your goals are not the same as the goals of those writing the math paper. The people writing the math paper, they're trying to prove a relationship and to present a mathematical model of something. And then the like appendix with some code, that's just an example, but it's not the point of the paper. But yeah. But I totally agreed like a while back that it's annoying how impenetrable math papers are sometimes, and how incomplete their code examples are. So, but yeah. I found that, like, even though there's a lot of notation and formal stuff in math that I just don't know, just reading the paper gives you so much more information than you might think. It's very, very often you like open a paper and you try to find the code, or you try to find a formula that you understand. Then if you don't do that immediately, it's easy to just give up, or like try searching somewhere else. But usually, at least if the math paper is well written, you can actually follow it all the way from start to finish. And I found that to be really useful, because math notation, especially, is not meant to be read by computers, so it's not consistent. They are like math notation is meant for humans to read, which means that there's a lot of custom applications of it. There's custom syntax. In some cases, you know, capital delta means different things depending on which paper you're reading and who's writing it and why. And so you can't really go into reading math expressions expecting them to work the same way the code does. Code and math expressions are just very different things. And so I think there's kind of a mismatch in expectations where, like, if you're a programmer and you're reading math expressions, you're kind of annoyed at how abstract it is, and you're annoyed at how ambiguous it is, and you're annoyed that it's not consistent across multiple different papers. But you could also look at it from the other end. If you are a mathematician, you might look at code and be annoyed at how goddamn verbose it is. Like, Jesus Christ, like, I can't even see the pattern here. It's multiple lines of a bunch of things. All of this could just be written as a single, like, summation. Like, what is this for loop thing? Why do we have to write int I equals whatever? Why do we have to add parentheses here? Why do we have a semicolon between each thing? Why is this even like presented as a process? Like, a mathematician could have a bunch of questions like that, where like code looks so verbose. And yeah, the reality is that just like there's mathematicians and programmers have different goals, and the notation they use is not always, it's just not always the same, and it's designed for different purposes. Like I think like code has, like, for example, variable names in code are very long compared to math. And I think it is a valid criticism of math that using a single letter for variable names kind of makes it really hard to understand the equation. But the other end of that is that you're not supposed to need to get reminded of what every single variable is. And the important thing is that you're supposed to be able to see patterns. You're supposed to see the structure and the relationship between all of these different things. And if you have a really long variable name, you're obscuring all of that structure that would be really valuable to see. Whereas in code is just a very different beast. And if you have a large code base, you kind of need to remind yourself of what every variable is. And you're not really doing that many, like, manipulating equations and shuffling code around in ways that are like based on mathematical patterns. And so it's just a very different use case. But I totally get the criticism of, why is math so unreadable? It should just be like code, but fundamentally they're different, and they have different use cases. Still annoying though when I just want to implement something. But anyway, I need more tea, so I need tea. Okay, I'm gonna go make some tea. I will be right back. Okay. Sorry if I've been bad at catching up with chat. If I miss a question, if you've asked something, just feel free to ask again in case I just missed it somewhere. I missed for a while. Have we passed the introduction? Yes, we're in related work now, so we're past the introduction. We've made it. We made it somewhere, you know. So we're making progress. Yes. Cattail. Probably yes. This is Salad. It's my son. Wait, do my shortcuts work? Can I do that? No, it does not work. Okay. That's Salad. His name is Salad. He's napping in a cat tree. Actually, all 3 cats are in the same cat tree right now. I can bother him by petting his tail. Oh yeah, he's a little bothered. Oh no, yeah, oh no, okay. Yeah, hello? Oh, you're bothered, I know. You're a little bit bothered. You're so bothered. Yeah. They all get along now? Oh, my bad, actually. I should not say all 3, because I do have a 4th cat. So. Hey. That's a whole story. I don't even know if I've told the whole story around the 4th cat on stream. But that's a story for another day. I have? Okay. Yeah, so there's a 4th cat. Gumpy. She's a cat that I couldn't find the owner of, and so yeah. I don't know what else to do, so I just have an extra cat right now. And unfortunately, Gumpy does not get along with 2 of my cats. But Gumpy does get along with Salad, the guy who's hanging off here. Are you still a cat, by the way? I noticed at some point you have only 2 ears. You know, the biggest issue is that wearing the cat ears kind of hurts my head after a while. So it was just... It's just a sad reality of physics, unfortunately. But so whenever I stream for a long time, I'm like, I don't know. I considered having like I wanted to commission that at some point. If I ever become like rich, then I would absolutely commission to like have a custom attachment thing made so that I could like attach them to the headphones instead of my head. That would be nice. Okay. Probably isn't too expensive. I don't even know. But it feels like something you would do if you didn't feel anxious spending money. So I'm sure you can get headphones with cat ears, but possibly they aren't very good headphones, and they also aren't very good cat ears. That's the problem. So it would be bad in both ways. Okay. Can someone remind me to get my tea in like a minute or so? Otherwise I'm gonna forget. And I don't want to forget my tea, because I need tea. Any advice on where to start become better at math? I'm also a Unity programmer, and I really came to a point where I need to be better at it for physics, shaders, and so on. it's really hard to tell without knowing exactly where you are, but this is such a boring answer. But usually, for me, the answer is that I just need to do it more. Like, if I want to become better at doing math, I just need to do math. If I want to become better at drawing, I just need to draw. Like, practice it. Like, try it over and over again and give yourself time and space to allow yourself to fail. And then, ideally, then the next day, try to come to some kind of solution rather than giving up. I don't know, but that's not very practical advice. It's very general advice. So, I don't know. What's with that smart T-Mug with Wi-Fi and API for notification? Oh, the T-Mug? Yeah. My T-Mug has Bluetooth support and it has firmware updates. But it's just a self-heating mug. That's all it is. Because I drink tea very slowly. And so my tea has a tendency to get cold when I'm like 25% through. So that's why I have a self-heating mug. That's all I use it for. So I don't really need any of the smart functions. So okay, I need to go get my tea. May I ask, what's your favorite programming language and why? C Sharp. C Sharp is great. It has everything I want and need. Every time I use any other language, I get depressed and I want to give up and just go do something else. I'm trying to think of if there's anything I miss in C Sharp where I'm like, ugh, I wish I had that. But it's just like tiny things. Like I wish I could break out of multiple nested for loops without using a goto. But that's like the most minor complaint that almost never ever matters. Cuz I can't just use a goto to break out of nested for loops. So that's not even a criticism. Can I ask what's the best resource you would recommend to learn Unity? I'm new to C Sharp and Unity. Try CodeMonkey, C Sharp, and Kitchen Chaos, but I feel like I'm rote memorizing instead of understanding. So I am very much someone who learns by doing, and I think that might be most people. So make sure that you're actually practicing the craft rather than just reading about it or just watching videos about it. I think there's a lot of people that kind of get stuck in the consuming content churn and hoping that somehow they're just gonna magically learn everything. But it's really important that you actually practice it yourself, because there's mentally you take a lot of shortcuts when you're watching educational content. And you might think that you understand something, but you don't actually understand it. But if you start implementing it yourself, that kind of collapses into the same state where like you know what you don't know once you actually try to implement it yourself. And so actually trying things out and practically getting hands-on practice with C# is probably one of the better ways to actually get familiar with the language. You're not going to get good at programming by just watching videos about programming. You're not going to get good at drawing without actually drawing. You can't just watch videos about drawing or even take an entire university course on like illustration. You're still not going to be a good illustrator unless you illustrate, right? which sometimes, I mean, sometimes it's hard. Sometimes you bump into a lot of problems, a lot of roadblocks along the way. That's just the nature of learning anything. And you really need to get used to that, pretty much. You need to get used to being bad at things and then growing. Which, depending on what it is you're learning, it can sometimes be easy, it can sometimes be hard. I think for me, if I'm bad at some aspect of programming, or if I'm bad at some aspect of math, I don't really mind. It's just like, oh, I was just not aware of a thing, and I can just learn the thing and then try it out, see how it works, experiment with it, and then I know that thing. The process of being bad at some piece of programming or math doesn't really bother me. But if I'm drawing something, if I'm doing illustration or painting, if I'm bad at painting, it's like a dagger directly into my throat. It's like, holy shit, I am cringe. This looks cringe. I am a horrible person. I don't want anyone to see this ever. This is the worst thing in the universe. Oh my god, torch it immediately. So like the emotional relationship you have with your creative work depends a lot on the type of medium you're doing. And like, I don't know, stuff like writing. There's something about being bad at writing that's embarrassing, to me at least. Or singing is another one of those things where like it hurts to be bad at it in a way that I don't feel about something that's a lot more like rigid, like mathematics and programming. So yeah, it varies a lot, and I think it varies like between people as well. I think some people do feel that it is embarrassing to be bad at code. I've just personally not really felt that much of that when it comes to programming. But yeah, for illustration, I absolutely do. And overcoming that like accepting that you are learning and that you're not perfect, like that can be a huge barrier. Sometimes it's prohibitively bad. Like it can be so bad that you never ever even try ever again. Like maybe you wish you could draw and you give it a shot and you felt so horrible about how bad it looked that you never even tried again. Like I think that happens quite a lot. Which is probably related to why I know you as a mathematician programmer and not as an artist. How so? Or like what reason? That's hard, especially for perfectionists like some of us. Yeah. Yeah, there is really something to the whole idea of sort of accepting your things that are cringe and trying to just like have a level of confidence over knowing that you are not that great at certain things. Because you're so afraid of showing your imperfect art. Oh, absolutely. Yeah. It's I have a very, 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 I don't know. There's something about that just like cripples me. Yeah. Math is rigid. Okay, well, sorry, Anon 1776. Did you want me to say rigorous? How about that? Does that help? Do you like that word better? Do you think rigid is negatively loaded? Then let's just say rigorous. That's something that mathematicians like. So there you go. Oh yeah, writing is another one of those where like if you're bad at writing, it kind of hurts. It's like, ugh. If you're writing like poetry, it just feels so much worse to write bad than to write some code that's a little bit bad. I don't know. It's really I think it has to do with like there's this inherent I think there's this inherent assumption that when you're writing something like a poem, you're supposed to convey a kind of message, or it's supposed to represent you in some way. But when it comes to programming, that doesn't really exist in the same way. Like, there is creativity and there is kind of like a personality to the way that you write code, but it's not really meant to convey a message or an emotion to whoever's like processing that piece of art, right? Like the art of coding is generally a lot more utilitarian. Like, it's supposed to achieve a certain goal. But yeah, so I think that's probably the reason why it feels so much less heavy to have like a slightly bad piece of code than to have a bad illustration, you know? Because an illustration is supposed to have more like either moral weight, emotional weight, more of a personal connection, you know? So like if that piece of art is bad, it's like, oh, that's because I'm bad, because this is supposed to be personal, and if it's personal, then the personal piece of creativity reflects bad on me, you know? CPU is judging you? Oh, that might actually be true. You know what? There we go. I don't even know if that's what you meant, but I've seen very bad code and it made me feel so bad. Like bad code from other people. I don't even know if I would feel like it makes me feel bad, or like have some kind of cringe watching someone else's or reading someone else's code. I don't know. In my mind, it's just a very, like, it just feels like such a detached, objective thing of like, oh, you know, this thing could be done in a better way. But I never feel like it's any kind of judgment on someone's personality or character. No, actually, you know what? There are cases where I would feel that. Sometimes some people have a very like idiosyncratic style of code. They might be using really bizarre spacing or naming of variables. I think for those things, I would actually feel some amount of that kind of like, cringe, I guess, at like, oh, they made some weird creative decisions here, you know? But if it's just that they didn't know how to do something in a better way, I feel zero cringe about that. It's just like, oh, well, I mean, they just didn't know, right? So that's fine, you know? But when there's creative decisions that I just super disagree with, then I can feel some kind of, yeah, I don't know. But I suppose, yeah, I suppose that can probably happen in math too. Like if someone writes a math paper and their justification for the proof is just god awful, or you can like tell that they're not like interested, but they're doing it anyway. Like then, for math stuff, I'd probably feel some amount of that type of cringe. But I don't know. I haven't read enough math papers to have valuable opinions about it. So. Okay. Also, yes, I did get my tea. Did you wake up one day and decided to learn about differential geometry? Is there more context here? So yes, there's more context. If you want a use case. So I am making a 3D modeling tool called HalfEdge. And HalfEdge is obviously going to be dealing with a lot of geometry. As you can see, this is a mesh, polygonal mesh, where you can manipulate vertices, move faces around, all the kind of stuff. You can also use my broken rotation code. Yeah, and there is a thing in a lot of 3D modeling tools known as soft selection. So if you select a vertex or even select multiple vertices, you want to have a kind of soft fall off so that instead of just moving these 4 vertices when you move them around, you also move some soft kernel around that, so you kind of get a soft bump that you move out of the mesh rather than just these 4 vertices. So that's known as soft selection. And I want to implement that, which is either very easy if I want to implement soft selection based on Euclidean distance, where like if this white S is a mesh, and I just get the Euclidean distance here in yellow, so the distance from point A to point B, and then I use that distance to put the like radius of soft selection boundary within, then it's pretty easy to implement that. But if I want to implement something like geodesic distance, then it gets more complicated. And trying to find the geodesic distances between, in this case, let's say point A and point C, is relatively non-trivial. It's sort of like a pathfinding algorithm, but in my case, I'm selecting a, half of, like, I could be selecting thousands of vertices, and then I'm going to get the distance to the remaining 1,000 vertices. So I can't do something like Dijkstra's algorithm from every vertex to every other vertex, right? That's not viable. I need a faster method for that. And so I am currently reading a paper about the heap method for calculating what's known as the geodesic distance from a set of vertices to every other vertex. And that involves differential geometry. So there you go. That's the story. If I remember correctly, libgl has a good implementation of that. Well, that sounds cool, and I'm not gonna look at that because I'm one of those losers who like learning things. So I don't just want to copy paste code. How's stream going? It's going pretty well, I think. I noticed I've been sitting weird. My neck is unhappy. They have documentation with the math details too. Gotcha. That might be useful, yeah. Like if I read to the end of this paper and I still don't get it, then it could be a good thing. Be aware that algorithm gives fairly poor results for some simple cases, like even 2 triangles, and most people subdivided the geometry first, which may negate some of the benefit. I mean, I do want to try it out first, and if it doesn't work, then I'll probably look at the refinement stuff, but I don't think I need refinement right now. I am reading both chats, so don't worry about it. It's just that I quite often miss stuff. I have absolutely no idea what this is, but I'm bored and this got recommended by YouTube somehow, so here I am. Welcome, Thin OT Mandresi, Thinaman. Oh no, wait, it's probably a French name. Thinon Mandresi, like something like that, probably. I don't know. Anyway, do you think as a non-math person I might be able to learn something if I stick around? I'm not sure. Probably not. This might actually be one of the most dense math things I've done on stream before. I'm trying to get through a math paper, which is takes a lot of learning about a bunch of notation stuff. But you know what? Feel free to stick around. I'm doing stuff with geometry right now. The goal is to learn about a specific method in order to find distances along the surfaces of a mesh. And that's, yeah, that's what I'm reading about. Okay, I forget, where were we? We were just looking at the iconal equation. So the iconal equation was basically just an ultra formal way to say that it's a function of constant speed away from some source where distance is 0. Okay. Can't you use polar coordinates to find the curve length? Then the problem is to find polar coordinates, because it's supposed to be length along the surface, not Euclidean distance, right? Okay. The prevailing approach to distance computation is to solve the iconal equation. So the gradient of the distance function, or the magnitude of the gradient of the distance functions, is supposed to be 1, which means it's just 1 meter per meter away from some boundary, here denoted gamma. And the boundary is just the place that's supposed to be 0 distance. So that could be a point inside of the thing, it could be a line, it could be a curve, or whatever. In my case, it's just going to be whatever vertices I have selected is gamma in this case. Okay. This formulation is nonlinear and hyperbolic, making it difficult to solve directly. Typically, one applies an iterative relaxation scheme, such as Gauss-Seidel. I recognize this. I'm just gonna add that to some words I want to remember. Plus an iterative relaxation scheme, such as Gauss-Seidel. Special update orders are known as fast marching and fast sweeping, which are some of the most popular algorithms for distance computation on regular grids. And some citations, and triangulated surfaces. These algorithms can also be used on implicit surfaces. Implicit surfaces, that's stuff like signed distance fields, for example, are usually defined as implicit surfaces. So if you want to define a sphere as an implicit surface, usually you would write that as something like, x squared plus y squared plus z squared equals 1. That's an implicit surface because you're passing in coordinates, and then you're basically saying, or rather, -1 equals 0 instead of less than 1. Like that would be a signed distance field for a sphere, and that's an implicit surface. So a lot of signed distance fields are implicit surfaces. Yeah. So you know what? Let's go to Desmos, and I can show an example. So if you have something like x squared plus y squared -1 equals 0. So this would be an implicit equation for the sphere. But you could also have an explicit definition, so that would be like a parametric equation. You can have a function of some variable t, and then this is like the cosine of t, and then sine of t times tau, for example. So this is also a circle, but in this case, it's parameterized with a variable that goes from 0 to 1. So that kind of gives us a vector or position around this whole sphere. So this would be a parametric equation, but the one at the top here would be an implicit equation. So that's what they mean by implicit surfaces, I believe. Did it say implicit surface? Did I close the... No, I have it here. Okay. Okay. So can also be used on implicit surfaces, point clouds, and polygon soup. I've only heard of polygon soup as a mistake. Like I've only heard it be described as the thing that happens when your mesh algorithm is incorrect. I've never heard it described as like a valid form of geometry. I'm guessing polygon soup is probably like it's a point cloud, but instead of points you have a simplex or something. Anyway, but only indirectly. Distance is computed on a simplicial mesh. Simplicial mesh just means 3D mesh for all intents and purposes in this case. Distance is computed on a simplicial mesh or regular grid that approximates the original domain. Right, so the original domain could be like a smooth surface or something, but you're using a mesh to approximate that. Okay, implementation of fast marching on simplicial grids is challenging due to the need for non-obtuse triangulations, which are notoriously difficult to obtain. I think I remember something about how, like, for 3D meshes, you can't guarantee non-obtuse triangulation. There's a... This is probably gonna come up. There's something when it comes to simplicial meshes, it basically just means mesh. You have triangles. It means triangle mesh, pretty much. So there is a concept in when it comes to triangle meshes that's called a Delaunay triangulation. And it's a certain notion of a mesh that is well behaved. So if we imagine a 2D mesh, I'm realizing this looks like a 3D mesh now. If you have a 2D mesh and it's triangulated in some shape like this, right? This mesh does not meet the Delaunay constraint. So Delaunay constraints is basically just like if you take any 3 vertices and then you draw the circumcircle, like the circle that passes through these 3 points, whatever that would be, something like that. Whatever. It's imperfect. I'm not perfect, okay? Don't judge my art. So if you draw the circumcircle for the vertices of every triangle, you want there to be no vertices inside. So in this case, it just doesn't meet the Delaunay criteria. So this is a non-Delaunay mesh. But if we flip this edge, so instead of triangulating this shape like this, we triangulate it like that, then we would actually meet the Delaunay criteria. Because now the circumcircle between these would be something like this, right? And the circumcircle for this triangle right here would be something like this. And there's no vertices inside either of these. This is known as a Delaunay triangulation. And Delaunay triangulations are really well behaved under a bunch of different algorithms. There's a lot of algorithms that kind of fail if you don't have a Delaunay mesh. And it just generally just improves accuracy if you have a setup like this. The center of the circumcircle must lie inside the triangle. That might actually be the better definition. Is that the definition? It might actually be. Rather than being about every other vertex. Okay, Delaunay triangulation of a set of points in the plane subdivides their convex hull into triangles whose circumcircles do not contain any of the points. That is, each circumcircle has its generating points on its circumference, but all other points in the set are outside of it. Okay. So that is the definition that I was using. I don't know which thing implies the other. Or if there's like... Or maybe one implies, yeah, I don't know. I'm not sure. The circumcenter can be outside the triangle. The top example, yeah. But isn't, yeah, actually, yeah, this is a valid Delaunay triangulation. Unless this would be, because I know that there's something known as like a constrained Delaunay, which I forget exactly what it is. But yeah, the top triangle here obviously has a circumcenter that's outside. Yeah, this triangle as well. Okay. Right, I was bringing that up because I mentioned non-obtuse triangulations, which is a slightly different thing, but I think they're getting at sort of the same idea. Like if you have a mesh that has, I don't know, most algorithms kind of hate long, skinny triangles. Like you can have like triangles that are like this. This is usually bad. Usually nobody likes long, skinny triangles. Algorithms don't like it. Rendering doesn't like it. I don't like looking at them if I'm editing this model. Like nobody likes skinny triangles. So usually those are to be avoided. Okay. Implementation of fast marching on simplicial grids is challenging due to the need for non-obtuse triangulations, which are notoriously difficult to obtain, or else a complex unfolding procedure to preserve monotonicity of the solution. Monotonicity just means it means non-decreasing, like it's only ever increasing or only ever decreasing. So like a monotonic function. A monotonic function would be something that's kind of like, this is a monotonic function, right? But this is not a monotonic function because it changes direction here, right? It goes down here and it just changes direction, right? There's also something like if it increases but then has a flat spot and then increases again, there's like a difference between strictly monotonic. So like this one is strictly monotonic, but the lower one is monotonic, but it's not strictly monotonic. Yeah, and I believe you can sort of, I don't actually know how much the notion of monotonicity cares about sign, but there is probably somewhere some distinction between if it's allowed to be increasing or decreasing. But you can have a monotonically decreasing function as well, like I don't know, the exponential function or something. So this would also be a monotonic function. Generally, it's kind of a useful concept for if you want to know if you can find an inverse to the function. If it's strictly monotonic, that means that the inverse has a single solution for every input or output. Like you can always find an inverse with unique values. But if it's not strictly monotonic, then there is ambiguity along this line if you wanted to find the inverse. So you can't always like find the inverse or root solve a function that's not strictly monotonic. Yeah. Okay, that's what monotonicity is. Which in the context of our distance function is a very it's very relevant, right? Because distance is a monotonic function in general, right? You wouldn't want it to like suddenly like shorten the distance without, you know, actually going back or something. Like you want that to be monotonic. Okay, so let's see. Or else a complex unfolding procedure to preserve monotonicity of the solution. So monotonicity of the solution in this case being the the distance value, right? So we want that to be monotonic. Moreover, these issues are not well studied in dimensions greater than 2. Right, so this would be distance functions in 3D space, and where like your boundary is a 3D. It would be like a distance function within a volume or something. So like a tetrahedral mesh or something would be the equivalent, and you want the distance inside of the shape as like a scalar for every volumetric point instead of like a point on a surface, for example. Fast marching and fast sweeping have asymptotic complexity of O and log n and O of n, respectively, but sweeping is often slower due to the large number of sweeps required to obtain accurate results. Okay, I'm guessing fast marching and fast sweeping are just like specific methods within the cited papers. Kind of sounds like the collision detection sweeps or iterations. I presume it's related to or similar to that. The main drawback of these methods is that they do not reuse information. The distance to different subsets, gamma, must be computed entirely from scratch each time. Also note that both sweeping and marching present challenges for parallelization. Oh yeah, they do not reuse information. The distance to different subsets, gamma, must be computed entirely from scratch each time. This is really relevant to this case as well. Because if it was the case that I only ever selected a single vertex when I wanted to compute the distance functions to every other vertex, that might not have been a problem, that it doesn't reuse information. But the moment I'm supposed to be able to select more than just one, then it would be really annoying if the distance functions for all of these all of the other selected points would have to like recompute a bunch of things rather than reusing all the stuff that this one already computed. So yeah, I think it's just saying that the heap method has a bunch of advantages because you can reuse some of the stuff that you computed. So you don't have to rerun the algorithm for every single vertex. That would probably make it way too expensive to run. So I think that's probably what it's saying. Also note that both sweeping and marching present challenges for parallelization. Parallelization is basically the idea that depending on, like, you might have some architecture where you have a bunch of different threads or computational cores that can run computations in parallel, and then you combine the information at the end. Like designing algorithms for the GPU. The graphics card is extremely parallel. And so if you can parallelize an algorithm, you can probably run it like orders of magnitude faster on the GPU than on the CPU. Because it's kind of like the CPU is like a squad or like 4 superheroes. But the GPU is like an entire army of very basic, stupid people who don't really know how to do advanced things, but they are many. And so if you can find a way to delegate tasks to your enormous army of people who can only do basic arithmetic, then you might be able to make certain algorithms much, much, much faster. Where you just have a lot of data you need to process, and a single person going from data point to data point to data point to data point is really, really slow. But if you can just like send that data out immediately to the swarm of bees that can just simultaneously do their one computation and then like combine it back into the end, that's quite often a lot faster. But it's not always easy to convert algorithms from a serial computation to a parallel computation. With parallelization, you kind of have a new problem of synchronization points and making sure that you're not like reusing or using old data or using new data where you're not supposed to and stuff like that. But yeah, parallelization is kind of interesting, and I'm probably going to have to do that. So if I, for a lot of this code at the end, it's probably going to be in a compute shader because this would be the best way to do parallel code. Because then I would just delegate all of the computation on mass amounts of data to the GPU. Okay. In my imagination, you just started to sing a science song, did I? Neat. I hope it was good. It's like one vampire versus an entire city of villagers with torches and pitchforks. Yeah, something like that. Are you open to code contributions for Half Edge? I'm not sure. I'm gonna have to think about that because Half Edge is gonna be commercial software, and so there's like license and liability questions that need to be answered if I have other people contribute code because it's not an open source project. Yeah, I'd have to think about it. I'm not sure. I do have plans on having plugin support though. So whatever the case is, it's supposed to be relatively extendable. Stuff like adding your own actions to it and yeah, stuff like that. Oh, okay. I need some more tea. I haven't been drinking enough tea. In the age of AI, Wikipedia is still the golden standard. Yeah. Yeah. I was wrong. Your definition is the correct one for Delaney. For heap method, the circumcenter should be inside the face, though. Oh, okay. So it's specific for heap method. Geodesic distance must never decrease as we move away from the source. Oh, yeah, that was the monotonicity condition. Nice to catch a stream. I was looping the fuck out. I don't know what looping the fuck out means. In your procedural geometry live course for like a week. I don't know if that's bad or good or bad, but neat. Will it be using the Unity job system and burst compiler and mono versus ECS? It's going to be a compute shader, so it's not going to be doing the CPU code. I mean, actually, I might do it on the CPU just because it's a little bit easier to debug. We'll see. I meant the engine as a whole. Right now, it's kind of a mix. Right now, I don't use ECS, but I do use jobs and the burst compiler and compute shaders right now. Okay. All right. Sorry if I'm going painfully slow on this paper. But I presume it's helpful if I explain some of these words like monotonic and parallelization. Hopefully it's useful. Oh yeah, you know what? I should actually write gamma because this whole set is what's known as gamma in these papers. Absolutely. Thanks for explaining. All right, good. How do you debug GPU code? You look at the colors. Just look at the colors that come out the other end, and then you're like, that looks good or that looks bad. Okay. Also note that both sweeping and marching present challenges of parallelization. Priority queues are inherently serial, and irregular. So serial is the antonym to parallel. So serial just means one after another, and parallel means simultaneous in the context of computation. And irregular meshes lack a natural sweeping order. Okay, I'm guessing the notion of like sweeping is probably specific to those other papers. It sounds similar to the. I know that there's like algorithms like sweep hole for convex holes, and then there's like there's similar sweep line algorithms for like the Voronoi diagram and stuff. I presume it's a similar type of thing where like you're sweeping some line or some plane throughout your data and then kind of constructing the solution from that sweep. Not 100% sure what a regular versus irregular mesh means here, but I presume it's similar to the Delaunay configuration. Like irregular mesh, it's a shitty mesh. You want your algorithm to work okay, even if the mesh is just garbage. Okay, Weber, etc., address this issue by decomposing surfaces into regular grids, but this decomposition samples the surface and requires a low distortion parameterization over a small number of quadrilateral patches, which is difficult to obtain. That sounds very annoying. Okay. So basically what they're saying is that if you have your 3D mesh, they're saying, what if we cut this up and then unfold it into flat pieces? And then we give each piece a rectangular region and say, this is a part of our domain that we want to do distance over. And then stitching them together in some way, which seems both annoying to compute and annoying to work with. Because you can't always unfold without distortion. Yeah, anyway. Requires a low distortion parameterization over a small number of quadrilateral patches, which is difficult to obtain. Okay. In a different development, Mitchell gave an O n squared log n algorithm for computing the exact polyhedral distance. Polyhedral distance from a single source to all other vertices of a triangulated surface. Oh, is polyhedral distance... is polyhedral distance where if you have a mesh like this and you want to get the distance from A to B, is that basically taking this route, like walking along the edges? Is that polyhedral distance? It sounds like that's what it's saying. Distance along edges can just use Dijkstra, so no. Okay. Polyhedral distance. Measures a separation between or within convex polyhedra. Does it have to be convex? That doesn't sound right. Is there a notion of polyhedral distance? Geodesic distance, I know what that is. I would assume the geodesical distance on a polyhedral surface, but then wouldn't you just call that a geodesic distance? I think it's on Polygon Soup. Oh. Yeah, the stack exchange thing isn't really asking about the term, though. It's asking about a specific case. Anyway, I don't think it's important in this case. I was just curious. I guess I could just look up the paper if I'm not lazy, but I'm gonna be lazy. They give an algorithm for computing the exact polyhedral distance from a single source to all other vertices of a triangulated surface. So, how do you pronounce that? Shirashki demonstrate that this algorithm tends to run a sub-quadratic time in practice and present an approximate O(n log n) version of the algorithm with guaranteed error bounds. Bohm and Cobalt extend the algorithm to polygonal sources. Oh, wait. Hold on. Do they just mean that polyhedral distance is not necessarily a simplicial mesh? That it could be like a mesh made of things that are not only triangles, that it could be like you could have pentagons and quads and whatnot. Maybe that's what they mean. I don't know. Anyway. Extend the algorithm to polygonal sources. Similar to fast marching, these algorithms propagate distance information in wavefront order using a priority queue, again making them difficult to parallelize. More importantly, the amortized cost of these algorithms over many different source subsets. Remember, gamma is the locations where distance should be 0. That's what this source subset gamma is. That's all that means. I need to it sounds like I'm saying that to remind all of you about that, but it's probably equally just that I need to remind myself of that because it's so formally written. Okay. Is substantially greater than for the heat method since they do not reuse information from one subset to the next. Right. So they don't reuse information from one subset to the next. That's probably just the thing where when you want to compute the geodesic distance, the computations that you'd make on the mesh, you're computing all the stuff all over again for every vertex that you're doing this with. So they don't share much data, but presumably, as far as I gather, the heat method actually does share a lot of data between these different vertices. So I think it's going to be kind of like you have your mesh, and then there's going to be like a pre-processing step where you compute a bunch of properties on every face or every edge or every vertex. Like you can pre-compute a bunch of things. I think it's going to involve computing the Laplacian across the mesh. And then once you get all of the geodesic distances, each vertex is going to be using this data instead of recomputing all of this stuff every single time. So I think that's what they're getting at with the heat method. That's the method that's in the paper that I'm reading. Right now, they're just talking about prior work on similar issues. Finally, although Suraj Sky greatly simplifies the original formulation, these algorithms remain challenging to implement and do not immediately generalize to domains other than triangle meshes. Closest to our approach is the reason method of Rangarajan, Gurumurti. I have no idea how to pronounce these names. Are these Indian names? That's what I would guess, at least. I don't know how to pronounce them. Who do not appear to be aware of Vardon's formula. What? You're just throwing shade. Like these guys in particular are just not aware. Jeez, okay. Rude. They instead derive an analogous relationship, phi equals negative square root of, What does it mean when there's a line through the H? I don't know what that means. H log, what symbol is that? Can't search for that symbol, what? Can I paste it here? No. What is this? Or is it just a V that's cancelled? Like a weird V? Oh, H bar. Yes. That's what I recall. I recognize that. Psi? Is it just pronounced psi? Like S-Y? Phi? Psi? No, this is phi, right? But this is... Or wait. Oh my god. No. I got it mixed up now, I think. I thought this was psi. No. Phi. This is phi, and this is psi. I think. Phi is the first one, psi is the second one. Okay. Cool. You know what? I need to write that down because I'm going to forget. Oh, phi. Oh, yeah, that's true. Phi and C. That's true. It's not phi. It's phi. Yeah. I now remember that. That's what Keenan Crane was saying as well. This is Obsidian, the note-taking application. Okay, phi. Is it C? Like S-E-E, or do you enunciate the P? I don't know. Okay. So negative square root h bar log of C. Yeah. All right. Between the distance function and solutions C to the time-independent Schrodinger equation. Okay. Cool. I'm not going to do physics. That's for other people to do. We emphasize, however, that this derivation applies only in Rn. Losers. They just derived the equation for Rn. They were simply not aware that you need to generalize it beyond every single Euclidean dimension. Gotcha. Okay. Where C takes a special form. In this case, it may be just as easy to analytically invert the Euclidean heat kernel. There's an equation for the Euclidean heat kernel. Oh, wait. Is this the heat kernel for... oh, that's cute. Is this the heat kernel for how the... like the Dirac delta evolves over time? Is that what this is? It has to be, right? Actually, I wanna test this. Let's do that. Let's go back to Desmos. Huh? Because that would be kind of cool. Although wait. X. I don't know what X is in this case though. Or wait, X and Y. Maybe I can just or no, actually, yeah, I don't know how to insert that, so never mind. Or maybe I can just shove in x squared here and it's going to work the same, but then no, because it has to have the log relationship here. X is the source. But then what is, because when it says phi here, phi, oh wait, this is the, oh wait, this is just the distance. Oh, hold on. Yeah. Okay, I'm stupid. Cool. Okay, yeah, no, we can do this in, we can do this in Desmos. I'm gonna do it. Okay. So it's a function of t, and it's, okay, 4 pi t, so 2 tau, it's not on alt tab, but okay, t to the power of negative n over 2 times exponent function of negative, I'm just going to say abs of x squared. You know what? Abs of x squared is a little bit redundant. Over 40. Okay. N. Oh yeah, wait. We have x and t in this case. I think I want x to be the variable and then t. Yeah. Oh, I think I know what this is. So this should look like heat dissipating. Yeah. Hell yeah. Oh my god, look at that. Still not sure what n is. Okay, that looks incorrect. This looks correct. Okay, cool. So I presume this is it starts out with the Dirac delta, I think, which is just the value is 1 at 0 and 0 everywhere else. And that's going to be like the temperature. And then this sort of describes how that temperature spreads out across the line over time. I think that's just the heat dissipation. Cute. I'm glad that worked. N is the dimension of your space. Would that be, so 1 for a one-dimensional line and then 2 for a surface? Okay. Moreover, they compute solutions using the fast Fourier transform, which limits computation to regular grids. To obtain accurate results for their method, their method requires either the use of arbitrary precision arithmetic, right, like you have like a arithmetic with like a big int for rational numbers or something, I presume. Or a combination of multiple solutions for various values of h bar. No general guidance is provided for determining appropriate values of h bar. Finally, there's a large literature on smooth distances. Oh yeah, this was the thing I was curious about. Which are valuable in contexts where differentiability is required. However, existing smooth distances may not be appropriate in contexts where the geometry of the original domain is important, since they do not attempt to approximate the original metric and therefore substantially violate the unit speed nature of geodesics. I'm not sure what they mean by the original metric. Are they talking about like the geometry of the original domain? I'm guessing that means this depends on extrinsic properties like distances between vertices. Unlike the heat method, which relies on intrinsic measures, where you don't actually need to know the extrinsic features, because the heat method uses the Riemannian metric in order to do intrinsic calculations. I think. I think that's correct. That might have been nonsense. Well, that's the way it fits together in my head right now. Okay, I need tea. That was a. I required 5 brain units for that. That's other work section. It's supposed to tell why they're all wrong. Yeah, or like justify your own existence, to put it in another way. Means the metric in that case is given is different from the one given by the embedding of your surface. Okay, I haven't quite worked out what embedding means. Okay, so if you probably know this, so I'm simply gonna ask. Okay, so if we have a parameter space, I don't know, some kind of parameter space, like an input to a function or something. So this would be a function that takes 2 variables u and v, and then there's some kind of surface or whatever in 3D space. Well, I don't know, something like that. Okay. Where does the word embedding come in here? Your surface has coordinates. It is embedded in R3, so it inherits a metric from R3. Okay. So you're basically saying this 3D object lives in a space that we've already decided is like a Euclidean or Cartesian R3 coordinate system. Maybe not necessarily Cartesian, actually. I don't know if R3 requires that. Wait, it's R3. In general, a manifold does not need to live in a larger space, such as R3. Yeah, because you could have some kind of, like a conformal map. Like you could have a parameter space like that, but then you have some wonky, some wonky kind of shenanigan. Like, I think a lot of like complex functions have a tendency to create conformal twisty shapes like this. So like this, so this would then also be an embedding? Is that necessarily true, or do you have to like bestow an embedding of R2 on this? I guess if it's a complex if it's a complex function, then maybe it wouldn't really be R2, it would be C, I guess. I don't know. Hello, Willstray. Welcome to whatever this is. Does half-edge deal with texturing? Oh, UV mapping? I am so excited for UV mapping, so I'm kind of saving that for later. So yes, there will be UV mapping, but not like texture painting, at least not for 1.0. Okay, so hold on. I was initially asking about the embedding. Okay, when you draw it, you are assuming an embedding or an immersion. yes. I don't know if it's so much that I'm assuming or if I'm defining. Yeah, I've gotten the impression that like if this is an embedding in R3, or is it actually, is it more so that like if I have a function that takes, you know, this 2D coordinate of u and v, so you kind of have these parameters passed into a function, and then the function then produces a shape in R3. Is it accurate to say that this function is an embedding of the maybe unit interval to R3? Is that accurate? A Klein bottle cannot be embedded in R3, but it can in R4. Embeddings is about not allowing self-intersection, at the very least, I think, right? So that's a more strict criteria, I think. I think you can define it either way. You usually define it using a metric. It has an intrinsic metric. If you define a Cartesian coordinate system, you define it as tangent spaces at each point. I guess I'm still not entirely sure. Or am I sure? I'm still not entirely sure what, like I feel like there's like a dependency problem in my head. I don't know when I don't know when or how metrics are defined or if they are derived. Like there's something missing in my head for this. So I guess if we take the case of my 3D mesh, it's not that I have a function that generates a 3D mesh, right? It's more so that I already have a 3D mesh. Like this is my starting point. So let's say that that's my starting point. Have I don't know, do I have a metric? Or is that unspecified? Or is metric specifically about making measurements on some manifold that's different from the space it's embedded in? Is that what a metric is? Like it's a kind of parameterization, or what is it actually? An important thing about it being an embedding is that you can just use the R3 metric as long as you stay on the surface and handle vectors properly. Yeah, but I've also gotten the impression that there's advantages to using intrinsic metrics that don't rely on the what I would presume is an extrinsic metric of R3. I don't even know if extrinsic metric is a phrase that makes sense. Embedding is a space that holds the object. So the two input parameters are the embedding of the 3D object as I understand it. If it was the case that it was a function that generated the mesh. Is that what you meant by that? The metric tells you the actual distance moved on a manifold when compared to flat space. I just feel like they're the same. But maybe that's because I'm assuming like if it's a parametric function, there's in a general case, it's probably not always the case that like some increase in v is going to be the same increase in the embedding. Like it might be squashed or stretched in various ways. So like it's probably similar to like arc length parameterization for curves, right? And so if I take this parameterization, then obviously there's some squashing and stretching that would affect the way that I would measure distances. But I feel like that's not due to the squashing. I feel like that's due to the general transformation. So maybe the 2D case actually doesn't really work the same way. And also, I don't even have a parameterization. That's not actually my use case. So I don't even know why I'm bothering with the parameterization. But I think, no, wait. I think the reason I'm bothering with this is because this is going to be relevant in the moment I get into like differential K-forms. That's when I don't really need a parameterization to get from like one point to another in terms of position, but I do need a notion of differentiating in specific directions, right? But it's also not really mapping a square to the whole thing. I don't know. There's a hole in my brain somewhere related to this that I'm missing. Your polygonal mesh is an approximation to the smooth surface, isn't it? In my actual use case, I already have the mesh. So the mesh is already defined, and there's no smooth surface that I'm approximating because it's from my 3D modeling tool, right? So the mesh embedded in 3D space is defined, and then everything else is stuff that I add on top or interpret through that geometry. For general metric, you don't really visualize the manifold, you try and visualize the metric. What does that mean, to visualize the metric? Actually, wait, hold on. Does a metric have... Let me think for a moment. Does a metric have anything to do with mapping? Like if I were to map this parameter space onto the mesh, does that have anything to do with metric? Or is metric kind of a separate thing that is only about measuring distances, basically giving a number to distances? Yes. Okay, so a mapping from a 2D parameter space onto a surface is also a metric, even without defining a distance function? There are maps that preserve metrics, but other than that, no. Um, okay, so basically you're saying um, it's possible that if I have a defined metric in this space, it's possible that that might not hold when I embed it in R3 using some function. But if I don't have a defined metric in the parameter space, and I have a map from this parameter space to R3, there's still no metric involved. Like metric is a separate thing. These maps are called isometries. Oh my god, I feel like there's so many words for isometry and all of those different things. Okay. You equip spaces with metrics to measure distances between points. Okay. I think that aligns with my understanding. I don't know if I understand isometries now, though. I bet this Wikipedia article is going to be very readable if I search for isometry. In mathematics, an isometry or congruent transformation is a distance-preserving transformation between metric spaces, usually assumed to be bijective. Oh wait, no, okay. Isometry makes sense to me. That's fine. But all the goddamn words for bijective, injective, oh my god, surjective, I don't like these words. They blend together in my brain. And I need them to stop blending together in my brain. So I feel like they're always deployed when I understand the least about what I'm hearing. Okay. So a distance preserving transformation. Okay. If the transformation is from a metric space to itself, it's a kind of geometric transformation known as a motion. Okay, so it's a rigid motion in that special case. Well, what about if it's different spaces? You're looking for manifold section? Okay. An isometry of a manifold is any smooth mapping of that manifold onto itself or into another manifold that preserves the notion of distance between points. The definition of an isometry requires the notion of a metric on the manifold. A manifold with a positive definite metric is a Riemann manifold. One with an indefinite metric is a pseudo-Riemannian manifold. Thus, isometries are studied in Riemannian geometry. Oh boy. Okay. Wait, I feel like I got a chat notification somewhere that I missed, or something flashed by. My life flashed before my eyes. Trying to understand isometries. I don't know what positive definite means. The positive definite. No, wait. Actually, maybe I do. No, wait. I do know this. Positive definite means that it's a property of your inner product. It's one of the three properties you want on your Riemannian metric, I think. I forget exactly what it is though. It's like if you do the inner product with a vector itself, it has to be it is only ever 0 if the vector is 0. Otherwise, it's never 0. Is that positive definite? I hope I got this right, because that means I learned something. Inner product space. This looks like it's maybe. Oh wait, hold on. Or maybe I mixed it up. I don't know if I got this right. I just thought it was did I think of something else? Oh wait. Yeah. No, I did get that right. Look at that. Look at that. That inner product, positive definiteness. If x is not 0, then the inner product between x and x is greater than 0. Which would hold for like the standard dot product. Oh my god. Okay, cool. Neat. All right. I don't know how many layers deep we're in. We were in isometries because I was wondering about oh yeah, metrics. That's what I was wondering about. Okay. So what does it mean? What does it mean for me to define a metric on this surface? Well, what does that mean? So I'm guessing the whole reason you would add some kind of metric to this is because I want to do equations in assuming some kind of two-dimensional space. But doing those equations in R3, it's possible, but it's kind of annoying. And because a lot of the things that I want to measure are intrinsic properties, like geodesic distance, it would be nice if we could work with 2D coordinates So we define some inner product known as the Riemannian metric. And as the moment we've defined the Riemannian metric, we can do work in this 2D space because this gives it some notion of like distance in this space. What's not entirely clear to me though is how you define this, like in practice. Like what do I do? Like what's the next step? Because clearly it's not just a dot product. And clearly it's not about unfolding the entire R3 embedding into a 2D space, right? So it feels like it's some kind of thing in between. Like Hilbert mentioned, if you're already embedded in Rn, you get one from that, and it is just the dot product. But that would assume I'm doing math in R3, which I don't think the heap method does. Like if I do stuff like, so I remember watching the discrete differential geometry lectures. This was kind of like the first step before doing almost any other mesh operation, because I think the Riemannian metric allows you to get differential forms, like differential K forms, and then it lets you compute a bunch of things using differential K forms, assuming a Riemannian metric, such that you get valid results without ever having to step into R3, I think. You don't. The construction of the matrices is just to avoid that. But that's for the... Isn't that just specifically for the discrete case, though? Which I guess is the actual use case. I guess the course that I was watching, they were going through the continuous case first. But they analogized all of the continuous operations into the discrete case. So a metric is a function that allows you to map from the flat paper to the orange wrapped paper. I don't think it is. I think that's a map, which is different from a metric, I think, right? What are you using this for? I'm using this to do soft selection for my 3D modeling tool. Or that's in theory what I'm going to do at the very end. So if I select a bunch of vertices, I need to compute what is the distance from my selection to every other vertex. That's what I need to do. Yes, in the continuous, it's much more complex. In the discrete, every face is flat, making it easier. Yeah. Yeah, because I think there is a case to be made that, like, I could solve this without ever getting into Riemannian manifolds and all of that complicated stuff. I could just grab the discrete geometry algorithms and just shove them into a function and then probably work it out. But part of why I'm doing this is also because I do want to learn these things. Is it like the Earth thing where you just work on a paper instead of on a sphere while keeping in mind that the metric is twisted? I think it's partially yes, I think. But I think you can have a twisted map without a metric. I think the metric is specifically that you give some notion of distance to your entire thing, but it's possible to have a twisted map without a metric as well, so they're separable. I think. Okay, I need to drink some more tea. Do you want geodesic distance? Yes, that's what I'm doing. Okay, so before we move on, I'm just gonna look at Keenan Crane videos.
Well,
hello, Keenan. Okay. I just want to see specifically the Riemannian metric stuff. Just to double check. Half edges. I already know what that is.
The dual complex, which actually...
I wonder where that gets introduced. Okay, exterior algebra. Distance, look at that. I think this is the lecture. Yeah, let's see. Okay, inner product. Now we're getting... okay, so this is still in R3. We're not quite at the Riemannian metric yet. Okay, we got k-vectors, Hodge star. Basis k-vectors. It is like legitimately disorienting to have looked into like geometric algebra to like get into k-vectors. Because it's so similar. Like these are just bivectors. These are the three basis bivectors. It's like it's so similar, but also slightly different in like unexpected places. It's kind of interesting to like get this different perspective on it. Okay, not this one. Where is it then? Is it differential forms, maybe? Okay, recapping K-forms. Oh, okay, hold on. Now I think that we're getting to the thing. Don't have to deal with Riemannian metric yet. Well, that's the thing I wanna get to. Okay. Gradient. Okay, vector derivative, directional derivative, gradient, differentials. I feel like differentials is where we... Yeah, it depends on an inner product. Product rule. Curl. Exterior derivative. What?
To see
Where's the
that is,
Riemannian
well,
metric then? Inner products. Is this it? Are we getting there? Maybe it wasn't as cleanly defined as I was hoping. Maybe it's like scattered all over the lecture series. I seem to remember that there was specifically like a thing about the Riemannian metric, kind of recapping the whole thing. But now it seems to kind of move on to other stuff. Unless it's the surface one. Ooh, no, this might be the one. Okay, hold on. Okay, embeddings. We talked about embeddings. If you embed a parameter space into R3, you cannot self-intersect. That's we've been there. Differential. Okay. Immersion. Okay. Riemannian metric. Here we go. Okay. This playlist looks neat. Would you recommend it? Yeah, this is a really good series. Search for Keenan Crane. It's got lectures on discrete differential geometry.
mean? Well,
Okay.
many of the quantities we care about on manifolds, that we care about on curves and surfaces and so forth, can ultimately be expressed in terms of little measurements of lengths and angles of tangent vectors. So for instance, at a point P, I might have a tangent vector x, a tangent vector y, and by taking measurements of these vectors, I get all the information I need about the geometry. These lengths and angles are encoded by the so-called Riemannian metric, which we'll typically write as lowercase g. G takes two arguments, x and y, two tangent vectors, and represents essentially just the inner product between those two vectors.
So x and y in this case, in the example manifold here, is x and y, are they vectors in R3? I'm guessing they are, right? Not inherently, but for your use case, you can treat them as such. Yeah, I was thinking like specifically in the example on the right here, where it's you have a 2D surface in 3D space. Like, would x and y in this case be like 3D vectors, pretty much? Are you trying to make a physics engine or just learning maths? I am making a 3D modeling tool. And I'm looking into stuff like this because I'm going to need to implement a bunch of geometry functions. And And one of the things that I need for this is to get the geodesic distance from a bunch of vertices on a mesh to every other vertex on the mesh. So I'm reading through a paper about the heap method for geodesic distance, and I'm kind of painstakingly stopping at every moment where there's a word or a thing that I don't understand. So we haven't gotten very far, but I'm working through it. Um, 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 each point has its own tangent space. The metric is a function from that point. Wait, what? It even says so on the slide that's on display right now. Wait, does it? I feel like I still don't quite know. I'm still not sure if X and Y is part of the 3D space. Like is because I know what tangent spaces are, but I don't know which order things go in here, because maybe I'm wrong, but I had the assumption that the Riemannian metric depends on which tangent space you're in. TPM is a tangent space of the manifold of P. Yeah, that makes sense to me. But the thing is, like, if it's a vector in the tangent space, it would be a 2D vector. But if it's a vector in 3D space, but along the 3D embedding of the tangent space, then it would still be a 3D vector. It just happens to lie on the tangent plane, right? And so I'm not sure, is G supposed to accept the two-dimensional vectors in the tangent space in and of itself, or is it supposed to accept 3D vectors in R3 in this case? I'm not sure which one it is. Actually,
Just like
maybe he says
are encoded
somewhere.
after Y.
Wait, someone said yes in capital letters, but I forgot what thing that was supposed to be yes or no. I forgot what I asked. You can't really think about the tangent vectors in the context of your embedded space, but yeah, you're correct. It'd be analogous to R2. I don't know the specific details. It doesn't seem like it makes sense to talk about tangent vectors that aren't tangent to the surface at P. I mean, it would be tangent in both cases. It's just a matter of like what space the vectors are in. Are the vectors in the R3 coordinate system of the like embedding or the space, or are the X and Y vectors two-dimensional and they're in the tangent space, not just happens to lie on the 3D plane, but they're actually defined as 2D vectors. You have two metrics to play with: the Euclidean metric of 3D space and the Riemannian metric of the 2D tangent space. That is, they're both in the tangent space and R3. Oh wait. I'm thinking about the tangent space as a two-dimensional space, but if we also have the surface normal, then the tangent space would also be a 3D space. But okay. All right. Okay. What? Photoshop? Excuse me? Okay. All right. I feel like either I am completely misunderstanding this, or I am very bad at asking the question that I feel like I'm trying to ask. Oh, actually, hold on. Let me draw. Doesn't super matter actually. Drawing vectors pointing towards the camera. It's not easy. Okay. All right. So, all right, we have some kind of world space. We can call it R3. I don't know, is this the embedded space or the embedding space? Is it embedding space? I don't know. I don't know what to call world space. Regular ass 3D coordinates. World space shenanigans, right? Embedding space. Is that it? Okay. I'm just going to write that down. What? Okay. And then we have some manifold M. Never heard the term embedding space, but maybe that's a thing. R3 is embedding space. Surface tangent space is embedded space. Okay. Probably want to use XYZ for the embedding space and UV for the tangent space. Probably a good idea. Okay. In which case, I need to do this. Otherwise, my brain is gonna just give up on processing. So. Wait, no, I got this wrong. Yeah, I got this wrong. I was looking suspiciously right-handed for a while. I don't like right-handed coordinates. Okay. We got basis vector x, we got y, and we got z, and we got u, and v, and w. So W is the normal, yes. So the Riemannian metric. It says G, and it accepts two variables. I'm going to call them A and B, or two vectors. I'm going to just call them A and B for now. I'm realizing that a basis is kind of probably a separate thing. But let's assume I've defined the basis for the tangent space. Is the vectors A and B, what basis do they use? Like, are they expressed in terms of UVW, or are they expressed in terms of XYZ? You can choose what basis to use. They're independent of bases. But then I don't know what the purpose of the Riemannian metric is. If it's just completely arbitrary. Like, there's got to be a point to using a Riemannian metric. I thought the Riemannian metric was a way to translate the notion of distance from and to these two different interpretations, or the spaces. Or is that wrong? If A and B are in the tangent space, then there are linear combinations of U and V. Yes. But are they? Like, are they in the tangent space? Like, is the Riemannian metric designed to accept vectors coming from any space, or is it designed to only accept tangent space vectors? Or does it depend on the specific map? It's defined to only accept tangent space vectors. Okay. So would it be accurate to say then that the Riemannian metric is designed to accept tangent vectors where W is 0? like A and B in this case, is it the case that A would, assuming there was a basis defined, it would basically be like you'd have U times some X coefficient plus V times some Y coefficient, right? So W is 0. Would this be the kind of canonical input data to the Riemannian metric? W isn't really in the tangent space as it is defined. I'm sort of assuming the tangent space is three-dimensional in this case. But it doesn't really matter, I think. I think it could go either way. But you only have W in an embedding. Oh, yeah. It's not defined when you're on the manifold because your space only exists in 2D. Okay. So is it always the case that a tangent space has to be a two-dimensional space? Hello? Hello, Misty? I suspect Freya is using the word 3D to mean embedded in 3D space with 3 coordinates rather than the linear algebra definition of dimension. Okay, I'm guessing this could also be a notion of like convention. Like by convention, tangent space is generally defined to only be 2D. And then the moment you have a third coordinate, you're kind of leaving the 2D space and you're jumping into the like extrinsic space again. The dimension of the tangent space is the dimension of the manifold. Is a polygonal 3D mesh a 2D manifold? All your meshes are 2D manifolds. Okay. You can have 3D manifolds, but all of your or no, wait, that was not the message I wanted to read. So I could have a knot in 3D space, and the tangent space would be one-dimensional because it's just a curve. Okay, I think I should just keep watching. Okay. I think some of my questions are probably answered by this. So I'm gonna back up a little bit.
Many of the quantities we care about on manifolds.
Also, I have Thor in my lap right now. In case you haven't noticed Thor. Look at Thor. Look at this boy. Wait, I think it's his birthday, like super soon. Maybe today, actually. Let me double check. Yes, it is today. It's your birthday, Thor. You. It's your birthday. Wait, how old is he now? Did he hit 17? I think he's 17 now. Let me double check. Yeah, he's 17. He's an old man. Okay. He does become invisible. He's a void. Sorry. Hey, look up. Yeah. Where do you go? Yeah, there you go. He's just purring. You had him all 17 years? No. So Thor. How long have I had Thor? Like 7 years, I think. And before, but I've only so Thor is my was originally my ex's cat. And she got Thor when he was 10, I think. Or somewhere around there, 9, I think. So Thor came from a shelter. So he was 9. And then I met Thor when he was around 10 or 11. Yeah. And then after me and my ex broke up, I decided to have Thor, or we decided that Thor would stay with me. Just because I have 2 more cats, and they were friends, and we didn't want to separate them. So, okay. Anyway, all right. Lecture time. Going back to movies. Wait, where's my scene? There we go. Okay.
Well, many of the quantities we care about on manifolds, that we care about on curves and surfaces and so forth, can ultimately be expressed in terms of little measurements of lengths and angles of tangent vectors. So for instance, at a point P, I might have a tangent vector x, a tangent vector y, and by taking measurements of these vectors, I get all the information I need about the geometry. These lengths and angles are encoded by the so-called Riemannian metric, which we'll typically write as lowercase g. G takes 2 arguments, x and y, 2 tangent vectors, and represents essentially just the inner product between those 2 vectors. Just like the inner product in the plane or in any vector space, except this inner product can change from point to point. Depending on which point P I'm sitting at, the definition of this inner product might be a little bit different. Okay, so abstractly, a Riemannian metric is a smoothly varying positive definite bilinear form. Okay, it's a smoothly varying inner product. That's nice, but where does this come from? Why are we talking about this?
Still doing this? It's been 5 hours? Yeah. Got a problem with that? What's are you judging me?
So this all becomes very clear, very concrete if we start thinking about what is the inner product, what is the Riemannian metric that comes from immersing a little patch into n-dimensional space. Now, by the way, I should also mention, this can be confusing just linguistically. The Riemannian metric is not the same as a distance metric in a point set. So you might have heard of this idea of
Wait, what was
trick
that?
But where does this come from? Why are we talking about this? So this all becomes very clear, very concrete if we start thinking about what is the inner product, what is the Riemannian metric that comes from immersing a little patch into n-dimensional space. Now, by the way, I should also mention, this can be confusing just linguistically. The Riemannian metric is not the same as a distance metric in a point set.
So I'm guessing this is not about like distance metrics as in the like Euclidean versus L1 versus like L infinity norms. It's not related to that, right? Or actually, hold on. Because I thought the Riemannian metric like I feel like this feels contradictory to me, but I'm guessing the difference here. Okay, so it feels like a contradiction that that information of length and angle is encoded by the Riemannian metric, but somehow it still can't describe point-to-point distance. So is it true to say that point-to-point distance requires more information, whereas the Riemannian metric is kind of the minimum information required in order to do differential forms? Like, we don't really need the concept of like subtracting 2 points within this space or whatever. What we really need is just some way to get differential information out of this tangent space. Does that track? And is that accurate, or did I miss the point? A distance metric is induced by the Riemannian metric. But then what do they mean by it's not the same as a point-to-point distance metric? You don't need Riemannian metrics at all to do differential forms, so they aren't required for that. Okay. My model of this is the Riemannian metric is just trying to generalize nice Euclidean space to more general spaces, but that requires changing things and thinking about tangent vectors and integrals. Okay. Point-to-point is global integrated distance. Riemannian metric is local infinitesimal distances. Yeah, yes. That is what I was getting at. But I was talking about differential forms. But I think it's more accurate to phrase it that way, yes. That it's, well, I guess differentials and infinitesimals are very closely related, but that's my mental model of it right now. Okay, all right, I'm going to continue.
So you mentioned this can be confusing just linguistically. The Riemannian metric is not the same as a distance metric in a point set. So you might have heard of this idea of a metric that says, okay, the distance from x to y is the same as the distance from y to x, and the distance from x to x is 0, and so on and so forth. That is not what we're talking about here. The Riemannian metric is something that measures tangent vectors, not pairs of points. Okay.
Yeah, that makes sense to me, because like a vector is like, it's fundamentally like a Like a tangent vector feels like a quantity of change, but point-to-point distance doesn't feel like it has anything to do with change. It's just a displacement related to position rather than the rate of change of position. But they're very similar. But yeah, the infinitesimal aspect of it, it feels like the Riemannian metric is there to give infinitesimal changes a metric, but point-to-point distances requires like an additional piece of information about measuring points or like getting differences between points, which is a separate thing. Okay. All right. Riemannian metric is like a two form. It takes two tangent vectors and return a scalar. But I don't know vocabulary. A form is antisymmetric, but the metric tensor is symmetric. Okay. You get the point-to-point distance by adding up all the infinitesimal changes. The Riemannian metric has all the info you need, but it's not directly a distance metric. Okay. That makes sense. Okay. Yes. Okay. I think I'm relatively aligned now.
Okay.
All right.
So a good way to motivate the Riemannian metric to build up our understanding is to consider just a little patch that's been immersed in space. We have our domain U. We have an immersion F that bends that patch into a three-dimensional surface. And here's the key question. Okay, if you can understand this, if you can get your head around this, then you're really on your way to actually understanding the idea of a Riemannian metric.
I'm on my way to understanding the whole thing. I'm almost there. I'm understanding it. Hell yeah.
So, if
ideally, maybe we'll see.
I have a pair of tangent vectors, x and y, on this little patch, how should I measure their inner product on the three-dimensional surface? Right. So remember that this map F.
Oh, right. Yeah. Okay. So the Riemannian metric allows you to express a bunch of operations without having to step into 3D space. So as long as you have a Riemannian metric for every point in 3D space, you can simplify a lot of equations and expressions by sort of using the Riemannian metric to transform your 2D data, which allows you to get the correct readout. So like, if you do the Euclidean dot product between x and y in this original 2D space up here, then it would be positive non-zero. It would be like, I don't know, 0.5 or whatever. But if you were to do the dot product between these two vectors in 3D space, it looks like they're orthogonal, so it would be 0. So in a sense, doing the dot product between these two vectors in 2D is incorrect because you're not getting the actual dot product for those vectors in the embedded shape. So doing it directly with these two vectors up here is incorrect. Doing it with the 3D vectors by transforming them or something is correct. But there's a third option of, instead of always transforming everything into 3D, we can use the Riemannian metric to do all of these operations without having to go to 3D. Is that correct? Is there someone who knows more about this, who can say whether or not that interpretation is valid? Okay. 1 thumbs up so far. Cool. I'm going to trust you, Hilbert XVI. I'm bad at Roman numerals. Also in a bunch of cases where there isn't just a way to go to 3D. Yeah. I think super technically you're using the same metric in 3D and 2D, but doing the dot product on the 2D coordinates is just a non-geometric thing. Yeah. I mean, in my actual use case, a lot of these complications kind of disappear because I don't have any fancy curved space and it's literally discrete. It's not even continuous. So there's a gazillion simplifications I'm going to be able to do. But I do want to understand this. So that's it. I do want to understand this. So I guess I do want to understand the continuous case as well, just because I want to.
Is going to stretch, right? So remember that this map F is going to stretch those little arrows out into three-dimensional space. They no longer have the same length. They no longer have the same angle between them, right? So for that reason, we should not just take the usual inner product in the plane. If we want to measure the inner product of these vectors as they sit on the three-dimensional surface, we absolutely should not just take the dot product of x and y in our 2D coordinate system. Why not? Well, a good way to think about this is we could have expressed the same surface using a completely different parameterization, right? And then we would have gotten a different result. Right? These two vectors in our other parameterization would look like two different vectors. If we took the dot product, we get a different.
Right, so this is what makes it powerful, the fact that you can use different parameterizations, but if you do operations using the Riemannian metric, you kind of normalize everything to function the same way. So in a sense, it is an intrinsic way to measure surface properties. And I'm guessing you can't do this with everything. There are certain things that are inherently extrinsic, but for certain surface operations, it's really useful to have a shared notion of what it means to get the angle between two directions, I'm guessing. Okay. All right. Well,
different result. Which one is right? Right. This is just not the right way to do it. Right. So the ordinary dot product in our local coordinates tells us nothing, really nothing, about the actual length and angle of these vectors on the surface. What we want to do instead is take these two vectors, x and y, push them forward into space using the differential, and then just take their usual inner product in R3. So we take the inner product of df of x with df of y. That is what defines the induced Riemannian metric. That gives us a new.
Wait, hold on. So is it that this, in this particular case, is the inner product the same as the dot product in 3D? So like, is this doing a 3D dot product between the differential of f of tangent vector x and differential of f of tangent vector y? Yes, by definition. Because I seem to remember that oh wait, okay, hold on. The bracket notation for the inner product is that always defined as the dot product, or is it sometimes defined in different ways? Yes, because these are tangent vectors. Right, so because my space is R3 that I've embedded this thing in, because of that fact, the inner product is the same as the dot product. But let's say I had a curved 3D space. I don't know. I have a gravitational curvature because Jupiter is sneaking up on me. Then the inner product would not just be some simple dot product. Then I would need to apply some extra transformation there, I presume. Maybe. Okay. Is it wrong to think of the Riemannian metric as literally just transforming it to the embedding space, transforming which Keenan Crane calls push forward, the D in DF, and then just doing the dot product? Not always, but like if it is the case that it's embedded in R3. Could this also be used for mesh editing and anisotropic mesh smoothing algorithms in half-edge? Yes. If I do have a good understanding of all of this, there's a lot of applications for mesh editing. Yes. There are Riemannian metrics that don't come from embeddings like in the video, but for surfaces, typically yes. But the metric is not dependent on the existence of a push forward. Right. Okay. The brackets don't always represent the canonical dot product. Here, the geometrical properties of the surface don't depend on F, but do depend on the inner product you chose in the ambient space. Right. So the ambient space is R3 in this case, and in probably all of my use cases that I'm going to have for this. So I can sort of assume that that's the special case that I'm in right now, I presume. Okay. That makes sense to me. I'm okay with that. I can work with that.
New notion of inner product for our planar patch that's different from the ordinary dot product.
Wait.
That is what defines the induced Riemannian metric. That gives us a new notion of inner product for our planar patch that's different from the ordinary dot product.
But I thought it wouldn't be in this case if it is embedded in R3. Then I thought the inner product would actually be the same as the dot product if we're assuming 3D space.
Okay? So the key idea to take away from this is that this induced metric, G, is accounting for all the stretching that happened as we went from the flat plane into three-dimensional space, but it encodes that information still in our two-dimensional coordinate system. Right? We now know if we have vectors expressed in 2D, how can we take a measurement of those vectors that's equivalent to measuring them on the three-dimensional surface? Okay, so hopefully you have a reasonably good feel for that geometrically. How do we actually compute this explicitly?
I kind of want to bring
So one way to do it is we can
shapes and
represent
do that.
everything using surface. Represent that map is using a two-reason. It's just what we get by applying the metric to basis vectors I and j. We can do the mental form.
Okay. I think I can now go back to continuing reading the paper. That was like we were like 3 layers deep on terminology that I wanted to understand. Okay. All right. I don't even remember where we were at in this whole thing. We were talking about the oh yeah, we were looking at the Euclidean heat kernel. Okay, finally, there is a large literature on smooth distances, which are valuable in contexts where differentiability is required. However, existing smooth distances may not be appropriate in contexts where the geometry of the original domain is important, since they do not attempt to approximate the original metric, and therefore substantially violate the unit speed nature of geodesics. These distances also have an interpretation in terms of simple discretizations of heat flow. Okay. See section 3.3 for the discussion. Okay. Distance to the boundary of a region in the plane or a surface. This is spoilers. We're not supposed to look at this one, but for some reason, images have to be appearing too early. Spoilers. Heat method. Okay. Now we're getting to the actual algorithm for the whole paper. All right. Our method can be described purely in terms of operations on smooth manifolds. We explore spatial and temporal discretizations in sections 3.1 and 3.2, respectively. Let delta be the negative semi-definite Laplace-Beltrami operator acting on weakly differentiable real-valued functions over a Riemannian manifold. This is a mouthful. Okay, I do remember the Laplace-Beltrami operator. Not exactly, but I vaguely recall that it's just the Laplace operator, but a little bit more generalized. Acting on weakly differentiable real-valued functions over Riemannian manifolds. Okay, Riemannian manifold in this case is just a normal-ass shape. A shape without shenanigans. It's just a standard object. In my case, a surface in 3D space. Okay. The heat method consists of 3 basic steps. 1, integrate the heat flow. So the change in temperature is equal to the Laplacian of the temperature for some fixed time t. 2, evaluate the vector field. X is presumably a vector field, which in my case would be a vector for every vertex in the mesh. So that would be the vector field. So evaluate the vector field. The vector equals, so the normalized, negative normalized gradient of temperature. And then step 3, solve the +1 equation. So the Laplacian of the geodesic distance is equal to the divergence of the vector field x. Okay. All right. That makes sense. All of this aligns with what I remember. So this is basically an illustration of all the steps. So the first one is to integrate heat flow. In other words, we define some kind of heat kernel, or no, we define a seed where in my case, that is basically the vertices that I have selected. That's the starting point. And then we're going to assume that every other vertex is cold. It has 0 temperature. But the vertices that I've selected are going to be hot. They have 1 temperature or whatever value is suitable. So we say that these vertices are extremely hot. And what the first step is here, U, is to diffuse this temperature over the mesh. So over the surface of the mesh, we're going to assume the temperature is just going to distribute, which we can do with some computational shenanigery, I assume. So that's going to diffuse across the mesh. And then we get this a scalar value that kind of represents heat. Then we get the divergence of that. So these two middle steps are very simple and fast to compute. I assume this is just local computation. The first one, U, requires a solver, but not these two middle steps. So this is just the gradient of temperature gives us these vectors pointing towards the nearest point on our heat source, which is kind of like they're pointing in the opposite direction. So they're pointing towards the source. Assuming we have diffused this across every vertex in the mesh, that means that every vertex is going to have some kind of vector. The ones that are close to the temperature source are going to be long. The ones that are further away are going to be short. But if we just negate all of these vectors and normalize them, we're going to get a vector field of unit vectors that point away from the heat sources. So that's effectively going to be a field where every vertex has a vector that says, hey, if you go in this direction, you're moving away from the selection. It might not actually be per vertex. It might be per face or per edge. I don't actually know how they choose to discretize that, but we'll see. We'll see. After we have all of these normalized vectors, they are going to point along it's an approximate. They're approximately going to point along the geodesic distance away from all of my selected vertices or the heat sources. Once we have those vectors, we can integrate those. So that's going to be solving the Poisson equation. And once we've solved that, we finally get the geodesic distance on the right. Those are the steps on a high level. Yeah. So that's these 3 steps right here. Okay. I'm going to write these down in here. I've forgotten how to type. I don't know how to use keyboards anymore. Okay, integrate heat flow. How do you do dots above a thing? Is it like above and then C dots, or no? Just dots or over dots? No. Oh. \dots and then. Wait, really? That's a weird syntax. Sure. Okay. So that is going to be delta U. Integrate heat flow. You know what? We're going to do it inline just like they did in the paper. Integrate the heat flow. Oh, that should be capital delta. For some fixed time t. Okay. And then evaluate the vector field. X equals negative not by u over, oh yeah, just normalizing that one. Okay, so do I want to, nah, it's okay. Okay, yeah, that's just, okay, so that's just the gradient of temperature normalized and negated. Okay. And then solve the Poisson equation. Delta phi equals nabla c dot, which is divergence of the vector field. Cool. All right. You're the shapes person. I am. Just wanted to say thank you for making such a great asset. Thank you for liking it. That's not something you have control over, but I'm happy you like it. Oh, okay. Right. So the function phi approximates geodesic distance, approaching the true distance as t goes to 0. So that is, okay, maybe not necessarily Vardon's formula, but it works in a similar way. I'm using Obsidian for my notes. Okay. Note that the solution to step 3 is unique only up to an additive constant. Okay. Final values simply need to be shifted such that the smallest distance is 0. Oh, okay. Right. So we're gonna get something that is where the iconal equation approximates 1, but the value at our boundary may not be 0. So we just need to subtract that. And then we're good. I think that's what this is saying. Although wait, would the value at each boundary location have the same value? It's kind of unintuitive to me, if that's the case. Maybe it is. Okay. Final values simply need to be shifted such that the smallest distance is 0. Initial conditions, u0 equals direct delta. Recover the distance to a single source point. Okay, so this is saying or wait, Dirac Dirac delta? I don't know. Okay, so this is saying the initial condition for our temperature is going to be the Dirac delta at every source point x. I forget if the Dirac delta is 1 or if it's infinity. Infinity. Okay, so it's an infinitely tall spike. Yeah. This is a weird ass function, but I get it. You know, I get why we need this. Okay. You know what? I'm just gonna remove the numbering so that I don't have to think about the numbers because I want to add the other things. Okay, so we have some initial condition of U0 is the Dirac delta. How do you do the weird? Oh yeah, it is just lowercase delta. Okay, I feel like in my case, this is just for a single point, right? Oh wait, okay, hold on. Recover the distance to a single source point, as in figure 1, but in general, we can compute the distance to any piecewise submanifold gamma. Gamma is our selected vertices, so the source of the heat. We can compute the distance to any piecewise submanifold gamma by setting U0 to a generalized Dirac over gamma. Okay, that's what we need. The figures 3 and 4. Okay. Okay. Okay, well, that just shows it. But what is the generalized Dirac delta? Maybe there is a Dirac comb? That's not what we want. Do I need to do something special, or can I just sum the Dirac delta for every vertex? Like, that would be my naive implementation, but I'm not sure if that's mathematically correct. You can just sum if it's a bunch of discrete points. Okay. I don't need to like divide by the number of points or something. Divide my infinite Dirac delta. I think the generalized Dirac delta is just a Dirac delta. So just like, okay. I feel like I'm making an assumption by summing them. But if you use a finite number of points, just sum or average, it's a bit more complex if it's a continuous curve. I don't think I'm gonna need curves. Like, that would be like if I select edges. I might actually need that. But it's a bit of a special case, and I'm gonna say that it's a user error for now. Like I might want to have actual like distance from edges rather than distance from vertices. And in that case, it would be a bit more complex. Okay. Well, okay, so I think for now, how mathematically incorrect is it for me to say that I want to get the Dirac delta of gamma? Is that like super incorrect? That's what it is in my head. I just wanted the Dirac function at every point. Maybe I should consider like a sum of I don't know. The sum of delta over delta and then no, sum over gamma and then I want like gamma n. Is this valid? Is this? I don't know. I guess the Dirac function, maybe it doesn't accept a list. So maybe this is more rigorous. I don't know, but it's a sum now. So with the caveat that this is apparently maybe only fine for points. Like it might be more complicated if I want to have a distance function to edges, right? Sum over n instead of gamma. Well, in this case, I'm just thinking like n is just every element of that's in gamma. Dirac x is a function that yields 0 outside of x and infinity at x. Okay, if the definition is that general, then I can just write delta of gamma. then this is sufficient. I will add that here then. Summing. Yeah, summation might only work for point sources. Okay. So that is our initial condition. Okay. We can set, let's see, user to a generalized Dirac over gamma. Okay. The heat method can be motivated as follows. Consider an approximation, U sub t, of heat flow for a fixed time t. Unless U sub t exhibits precisely the right rate of decay, Vardon's transformation, U sub t, I always forget these arrows. The arrow to the right, this is not 2. Is it implies or something? Vardon's transformation, U sub t, arrow to the right, square root of -4t log U sub t will yield a poor approximation of the true geodesic distance phi because it is highly sensitive to errors in magnitude. Okay, so that's the thing we're not doing. The heat method asks for something different. It asks only that the gradient of U sub t points in the right direction. In other words, it's parallel to the gradient of phi. Okay? Magnitude can be safely ignored since we know from the iconal equation that the gradient of the true distance function has unit length. We therefore compute the normalized gradient field. X equals negative gradient of distance normalized. And find the closest scalar potential. Find the closest scalar potential phi by minimizing the integral over, let's see. I'm not entirely sure what this integral means, but it's like we're integrating over the manifold of the gradient of geodesic distance minus the normalized gradient field squared, or equivalently by solving the corresponding Euler-Lagrange equations, the Laplacian of the geodesic is the divergence of the normalized gradient field. Okay. I don't know which one of these they're going to do, so I'm just going to write notes of the one that they actually do. So it's like maps to. Oh, right. Okay, U of t maps to. Okay. So this is kind of like an alternative notation for functions, sort of. Okay. The overall procedure is depicted in figure 5. I think that's the one here. Yes. We have seen that one before. So, all right. We discretize the heat equation from step 1 of algorithm 1 in time using a single backward Euler step for some fixed time t. In practice, this means we simply solve the linear equation identity, which I presume is just 1, identity minus delta time, right? Wait, is that delta time? I usually don't see it written in that order. Yes, I think that's delta time because I think. Or wait, is it the Laplacian? But then the Laplacian of what? Delta is the Laplacian? But there's a. Okay, but there's a parenthesis that's closing the Laplacian immediately. It's a Laplacian of u sub t. Okay, this is a weird notation. Is this like incorrectly written, or is this like? Because I was like, okay, so this would be our delta time, but it's an operator acting on u sub t. Okay, it stands for u sub t minus t times the Laplacian. Okay. So this is just a notational shorthand. So like you would distribute u sub t to the right-hand side of both of these terms. So it would be 1 times u times t, or u sub t, 1 times u sub t minus the time multiplied by the Lagrangian? Oh my god, I feel like I'm dropping out words. Not Lagrange, right? Or am I forgetting? Laplacian. I don't know why Lagrange popped into my head. There's too many math people that starts with L. That might be a shorthand notation for the backwards Euler step. Well, I'm not sure. It's common in partial differential equations to write it this way because you're treating the entire thing in the parentheses as one operator acting on the function. Okay. All right. Lagrange mentioned in a paragraph up. That's true. That's where that came from. You are correct. I was poisoned by previous context, okay? How was I supposed to remember Laplace when Lagrange just like kicked open the door without my consent and just like announced his presence? Okay. So I presume this is just like I distribute u sub t to these two terms. There's nothing more to it. So this does mean the Laplacian, right? Or is it written this way because we're going to need to arrange it into a linear solver or something? Or yeah, it is written in a pretty confusing way. Because like if you're doing like discrete time stepping, usually I see the delta in front of the t, and it represents a finite change in time. But I don't think that's what it means here, because we're not considering changes in time. We have absolute time, because we have a function u sub t, which is time, not delta time. And so this is specifically the notation for the Laplacian, because nothing has been said about that otherwise. So I should assume that, right? Okay. Okay. All right. I'm just gonna write that equation. So this is right. So that's after the initial condition. Okay. So we've got the u sub t. U sub 0 is the right-hand side, U sub t is the unknown. Right, okay. I'm guessing that's why it's written this way, because in a linear solver, we want to arrange it such that, yeah, we have the form ax equals b, but it's not obvious to me how I would calculate this independently of, of this, because I thought this operator requires something on the right-hand side. So it's kind of confusing if I'm supposed to know what this is without actually applying this operator. To me, this almost reads like having a division symbol here. And it's like, well, t divided by what if I'm supposed to evaluate this independently? Okay, I don't know. That's kind of confusing, but I'm guessing it's going to make sense at some point, or I just don't get it maybe. Okay, so u sub t is the okay, I'm guessing that's what we're solving for. Yeah, because u0 is the initial condition that's known. And t is known because that's provided. And I'm guessing there's going to be something with the Laplacian where we pre-calculate that across the mesh or something, and then we get a linear system where this magically works out. Okay, so we've got t times delta, which is the Laplacian then. Okay, so this is a take a single backwards Euler step for some fixed time t. Okay, sorry, Euler, for not using capital E. Right, that's equal to u sub 0. ID is just the identity matrix. T is a small value. Oh, it's a matrix? Okay. Sure. But you know what? I feel like one should implicitly cast to the identity matrix if you multiply it by the concept of a matrix. Okay. In practice, this means we simply, okay, all right, we simply solve the linear equation, yada yada, over the entire domain M, where ID is the identity. Here we still consider a smooth manifold. Spatial discretization is discussed in... It's just not discussed. Oh wait, section 3.2. Yes, okay. We can get a better understanding of solutions to equation 3 by considering the equation 3. Which one is that? The one we just looked at. Okay. We can get a better understanding of solutions to equation 3 by considering the elliptic boundary value problem. Okay, so identity minus t Laplacian over... Wait, is this still u? Why does it look like it's a v now? Wait, hold on. Why did it turn into a v? Okay, maybe just to separate the two. Okay. Times v sub t equals 0 over on the manifold. Oh, I'm guessing this means it's 0 everywhere on the manifold that's not part of gamma, which is our selected vertices. So M accepts gamma. And it's supposed to be 1 at every gamma, which basically means set it to 1 at our selected vertices, set it to 0 everywhere else, I think, right? Okay. Which for a point source yields a solution v sub t equal to u sub t up to a multiplicative constant. Okay. That's a Dirac thing. Yeah. Well, Dirac is infinite at all of these points, but here we're setting it to 1. Okay, as established by Vardan in his proof of equation 1. Am I supposed to just know the numbers here? Equation 1. Oh, Vardan's formula. Big surprise. Couldn't you just have said that instead of writing equation 1? Jeez. Okay. Okay, as established by Vardon in his proof of equation 1. Okay, v sub t also has a close relationship with distance, namely the limit as t approaches 0. We have the negative square root of time over 2 times log v sub t is equal to sine distance. Okay. Oh, away from the... Wait, v sub t, namely away from the cut locus. Wait, the cut locus, that's like the inverse. Okay, maybe that's okay. This relationship ensures the validity of steps 2 and 3, since the transformation applied to v sub t preserves the direction of the gradient. Okay. I am not entirely following here. I think I think part of the issue is that I just never solve linear systems. So like I think if someone who does that often reads this, I feel like it's just implied that you're just supposed to know how to use a solver here. So oh, that's a lot of messages. Hold on. Perhaps we're making an even outmatching the debate energy of destiny, but saying the matrix 2 is better than the matrix 1. That's not me. That was someone else. Oh, what was her name? I don't remember her name. I was only in that conversation for like 20 seconds. so the person who did most of the talking was not me. But yeah. So feel free to send those messages to her. I forget what her name is. Deeds something? Yeah, something deeds. Yeah. I was mostly disagreeing with deeds towards like the last like 20 minutes of that 3-hour conversation. So, okay. All right. So what is this actually? Is this just an example of why it works, or is this like the actual procedure that you would do? It kind of sounds like this is just an example or like explaining why it works, but we're not actually doing this calculation. We're still solving this, I presume. I might be misreading that though. But it sounds like this is just like explaining why it works. My bad. I'm sorry. No, you're fine. you're good. I mean, I was in that conversation. I just didn't talk much because I was very tired. Love your video on Bezier curves, absolute cinema. Thank you. Happy you like it. I think to solve it, they use matrices to represent the Laplace Beltrami operator as some sort of a transformation matrix. Is why they use the identity. Okay. We are doing 4. Okay. But are we though? Because the Dirac delta is kind of like this, but it's infinite at here, right? It's infinite instead of 1. Anyway, maybe they're gonna say later. We'll see. Wait. Loves your video, but he hates your math and matrix 1 over 2. Well, I mean, I don't have strong opinions about the Matrix movies. But the Dirac delta does not exist in computer. No, but I presume they're gonna integrate using discrete versions of all of this. That's what I'm presuming, at least. It's not infinite because it's a Dirac measure. That hasn't been explained anywhere. It's so where does it say that this is already integrating the U? That's why we use V sub t instead of U sub t, and there's a constant factor. Okay. Okay, so this is but then what was the point of bringing up the Dirac delta in the first place then? If we're gonna replace it with 1 down the line anyway, why would we even mention the Dirac delta? Can get a better understanding. That feels vague. That feels a little vague. Is the U sub 0 supposedly takes 1 in the subset gamma and 0 elsewhere. That's the definition of the Dirac measure. Sure. And I get that that's what's happening here, but it's not clear to me that this is what you should do in this equation. Because it kind of feels like, oh, we can understand the solutions a little bit better by just considering these things, by the way. It sounds like it's just an explanatory thing rather than this being part of the actual algorithm. But we didn't? We didn't what? I believe Dirac delta is only used here to generalize the concept to a continuous domain. Okay. And I feel like the point that they're trying to say here, I feel like they're trying to say the choice of value for V sub t literally does not matter as long as it's non-zero. I'm guessing that's what they're saying. So whatever you choose, it's just going to be the same thing up to some constant, and because we're normalizing at the end, it doesn't matter. Right? But we didn't get a better understanding. Yeah, maybe I'm just being too implementation brained. I'm like, but which one do I implement? And I'm supposed to just get it? Okay. So I'm guessing equation 4 is the equation that you're supposed to work with when actually solving it in practice then. Okay, so are we giving up on U sub t? Or no, okay, so U sub t is the continuous version. V sub t is this alternate version, which is the same, but there's some constant offset, multiplicative offset over the whole thing. Okay, so I think this is basically saying just do this, because it's going to give us something that is fine to just normalize later anyway. So okay, valid. So basically what they're saying is that this can be solved through the elliptic boundary value problem. Is that can it be solved through, or can it be solved by considering? These are the complicated questions. Okay, so now we're doing V sub t equals 0, where outside of gamma, and it is equal to it's equal to 1 at gamma. Okay. Okay, this is bothering me. Begin. Align. It's gonna look great at the end. I promise. We got this. We just need to persist. Okay. Lining things up. We need some text. Remove some formatting shenanigans. Okay. I think that can be, or no, can it not? Okay. Wow. Okay, Obsidian, this does not spark joy. I guess I'll have to do that. Okay, cool. So this gives a it's a solution that's off by some multiple, but it's going to be fine because we're normalizing it, I think. Is there supposed to be a comma or a dot at the end of the formulas? I don't actually know what the standard is, but I feel like quite often I see dots in various places and I have no clue what the standard is for that, or if it means something everywhere. But in that case, I missed a lot of stuff. Note that by diffusion, U sub t on gamma will not be equal to U sub 0 on gamma. We need to keep the value on gamma so that the source will end with distance 0. I thought the way that they phrased it earlier, they said that like you would compute the distance values, but it's going to be offset such that it's not 0 at gamma, but you can just shift it later. But maybe this is later, and this is where we're supposed to shift it. Okay. All right. I don't know. I don't think I need to write this down. So I don't know if it's actually used. Because I'm pretty sure like once we've solved this, we don't actually do this transformation. I think all we do is we grab the gradient and then we normalize it. So I don't think we need this transformation. Okay. Spatial discretization. This is where things are finally going to get easier instead of harder every second. Is it effective to study from papers? A lot of hidden prerequisites compared to lectures and textbooks. I don't know. I just wanted to learn this, and whenever there's something I run into that I don't understand, I'm gonna try to understand it and move on. I don't know. I mean, I watched a few lectures from Keenan Crane, who was one of the co-authors of this paper. So I have some background, although those lectures are a lot more broad than this and a lot more complicated. So I didn't like pick up that much of all the more complicated stuff. But yeah, this is like the first time I'm trying to get like a practical application of some of these concepts. But in terms of effectiveness, I don't know. I guess it depends on what you're optimizing for. In terms of if it's effectiveness in terms of implementing the algorithm that I want to implement in the end, then this is extremely inefficient. This is super inefficient in terms of just getting an algorithm working. But my goal is not to just get an algorithm that works. I want to understand the algorithm and implement it myself. So yeah, so I'm optimizing for learning, not just the time until an implementation is there. Okay. In principle, the heat method can be applied to any domain with a discrete gradient, divergence, and Laplace operator. See that they just line them all up here. That's nice. Thank you. What about effective to understand at all? Each mentioned formula algorithm, their derivations. I don't know. If you know a better method, let me know. I guess I don't have a teacher I can just like pull out of a box. All right. Note that these operators are highly local and hence do not exhibit significant cancellation error despite large global variation in U sub t. U sub t. Wait, how is that different from? Or no, wait. U sub t is the heat. That's not. Yeah, right. It's not distance. It's the temperature. Okay. Highly local do not exhibit significant cancellation error despite large global variation in U sub t. Okay. Wouldn't you say understanding it does save time longer term, especially when extending and debugging compared to quickly implementing to get something working? Potentially, but I don't know if that's the case. But it's possible, yeah. Okay, simplicial meshes. That is actually, that's almost. Um, that is almost what we have, but I actually don't have simplicial meshes here. I have, I don't know what they're called, polygonal meshes? Because I have quads and you can have n-gons. But I think it is relatively easy to generalize to n-gons, and if not, I could just triangulate it. So that should be fine. Oh, you know what? I just said I don't have a way to just pull a teacher out of a box, but chat has been really helpful. So in a sense, I sort of have a box on my screen where there are some teachers, and I really appreciate y'all who actually understand these things and are helping me understand these things. So thank you. Okay, simplicial meshes. Let you I forget, is this set is a part of oh boy, okay. What's V here? I don't know what V is. Oh wait, it's the vertices, I'm guessing. I'm guessing it's like that one Euler thing where you enumerate edges and vertices and faces and you get like a number. So I'm guessing it's the same syntax as that. So V is just the vertices. Okay. There's a little bit of a syntax happening here, but I'm going to assume I know what he means. Specify a piecewise linear function on a triangulated surface. Okay. So does this are they talking about like the hat functions here? Or not entirely sure which piecewise linear function they're talking about. Okay, anyway. A standard discretization of the Laplacian at a vertex I is given by... Okay, so let's see. LU. What does that mean? Is this just like a confusing shorthand for the Laplacian? Why not write this as Laplace operator U sub I? What's with the parenthesis situation? Okay. So that is equal to 1 over 2 times a sub I. Okay, so a sub I is 1/3 of the area of all triangles incident on vertex I. Okay. It's the discrete Laplacian. Oh, okay. They mean that we're going to only consider functions that are linear in each face. Okay. That seems not inherent, but it makes sense. Yeah. Okay. Okay, this formula, or like at least the notation here, I think is important to remember, because that is That feels very non-standard to me. Oh, where would this be in my... This feels like a pre-processing step. I'll just add it outside. Okay. So this would be calculating the discrete Laplacian. Across the mesh. All right. This notation is so weird. I feel like math is just putting parentheses wherever they want to. Just there's no. I feel like there's no notion of consistency there. It's just like, well, here it's kind of defined this way. It's like, okay, you just have to like accept. You just have to accept life this way. Okay. So we have 1 over 2 a sub I LU is a scalar field, not a vector. It's a scalar per vertex. That makes sense to me, yeah. But I don't understand why the notation is written this way. Like, I would have expected, like, why is it not written, like, delta U sub I? Like, this makes way more sense to me. Because then it would look like the Laplacian of the heat function at vertex I, right? Like this would make sense to me. But this like parenthesis LU and then the sub is outside. It's like I don't know. I don't know. U is an array of scalar values, not an actual vector. Yeah, that makes sense for me. I'm just interpreting that as like a value at each thing. Isn't it a vector because L is a matrix? Is L a matrix? Oh, that's true, actually. We can express this operation via a matrix. Ooh, okay. This sounds like we're getting into like specific data structure layout stuff. Okay, L is a matrix and the equation is just the action of L on U. Okay. They use L instead of delta to emphasize the fact that L is discrete. Also, U and LU are vectors with index I corresponding to vertex I. What do you mean by LU is a vector? Because I thought this was a matrix multiplied by U? Maybe? It kind of feels like they're combining a lot of operations into a single matrix instead of doing them separately. LU equals L times U? Yes, but a matrix times a scalar would be a matrix, not a vector, right? Unless we're like talking about vectors in the sense that like matrices are vectors or I might have basis vector brain, where I assume that a vector is only a vector if you have coefficients multiplied by a basis vector. And I think it's illegal to call a row matrix or a column matrix a vector or like a column vector, because that's not a vector. That's just a bunch of floats or reals. Okay. Okay, I'm just gonna read on because I feel like I am otherwise gonna start guessing too much. Okay, so we've got 1/2 times the 1/3 of the area of all triangles incident on vertex I. So just take all the triangles around that are connected to I. The sum is taken over all neighboring vertices J. Okay. And alpha ij, beta ij are the angles opposing the corresponding edge. Okay, so for each outgoing edge, just kind of cycle through all of those edges, find the angles that are opposing that edge. Then you get the cotangent of those, add them up, multiply by u sub j minus u sub I. Oh wait, yeah, because u sub I and u sub j is known at this point, right? Or wait, are they? I thought that was what we were solving for. Hold on. Aren't these unknowns? Or does u mean something else now? Okay, I'm a little confused by that because I thought these were unknown. Okay, I'll pretend that's fine. We can express this operation via a matrix. L equals A inverse. Wait, the area of is it a matrix containing all of the triangle the areas around each vertex over 3? Are we representing that as a matrix and then inverting it? Is that what we're doing? Times L sub C. Okay, I don't know what that is yet. Oh, where A equals, I guess, real numbers of a V by V matrix, where V is the number of vertices. So is that it? So this is like it's a matrix of every pair of vertices. Or at least, oh wait, it's a diagonal matrix containing the vertex areas. Oh, yeah, it's literally just that. Okay. Vertex areas and LC is the cotangent operator representing the remaining sum. Okay. Heat flow can then be computed by solving the symmetric positive definite system. All of this. Okay. So, we're trying to define L. We get it from that expression. Okay. UI and UJ are unknowns. We're writing that equation for each vertex and combining all of the equations into a matrix equation. Oh boy. Okay. My like optimization brain is like we're just tossing around these gigantic matrices everywhere. It's like, oh, is it going to be mostly empty? We're just going to have a diagonal set of entries. That's so wasteful. I'm going to need a data structure for this. Ugh. Okay. All right. Heat flow can be computed by solving the symmetric positive definite system. So U is our unknown. All of this, is this known? Wait, is LC known? LC is what? Oh, the cotan operator. Wait, operator. How? I mean, isn't this the cotan operator? Wait. Because we have that there. Okay, A is a diagonal matrix containing the vertex areas. Optimize later? I probably will, yes. I think you need to look up simplicial complex. Nope. I know what those are. LC is a stiffness matrix. It encodes the connectivity of the mesh. That lives in a whole other data structure. Okay. I feel like those terms should be used here. Like I haven't seen connectivity or like stiffness or what was the other one? Oh, the mass matrix. Maybe they're going to say that later. Okay, heat flow can then be computed by solving blah, 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 blah. So this, we're back with the Dirac delta. Okay. Wait, no, Kronecker delta. Hold on. Did we just swap out Dirac with Kronecker? Wait, but oh, okay. Yeah. So that oh, that's just saying it should be 1 at the vertices, right? I usually don't see the Kronecker delta used for that, but I guess you could. Usually it's like an alternation thing. Like you have 2 indices that are like combining, but okay. Okay, a Kronecker delta already gives the integrated value of a Dirac delta. Sure. Okay, the gradient in a given triangle can be expressed succinctly as okay, so the gradient of u would be let's see, AF is the area of the face, and then we iterate over presumably the the edges, the vertices and their opposing edges, and then we do the cross product between the normal direction and is EI normalized, or is it just the vector? N is its unit normal, EI is the ith edge vector. I'm going to presume it's not normalized then, because it is specifying unit normal for the face normal. Okay. All right. N is its unit normal. EI is the ith edge vector oriented counterclockwise. Well, we'll see about that. I have a left-handed coordinate system. And UI is the value of U at the opposing vertex. Okay. The integrated divergence associated with vertex I can be written as wait, where did X come from? Oh, wait, XJ. Oh, it's the or no, wait, what is X here? The integrated divergence of what? Divergence of oh yeah, it's got to be the divergence of U, right? I'm guessing that's what they're talking about. So the integrated. Oh, they mention it later. Oh, okay. Okay, where the sum is taken over incident triangles J, each with a vector X sub J. Okay, so that is this right here. Okay, so we have E1 and E2 are the two edge vectors of triangle J containing I. Theta 1 and theta 2 are the opposing angles. All right. If we let B, who is B? Oh, the vector of integrated divergences. I presume B is just the variable name we're associating with the vector of integrated divergences of the normalized vector field X. And the final distance function is computed by solving the symmetric Poisson problem, where we have L sub C and our desired value, our unknown, our geodesic, equals B. Okay. Oh boy. Oh shit, polygonal surfaces. This is actually relevant. I'm going to need this. For a mesh with not necessarily planar polygonal faces, we use the polygonal Laplacian defined by Alexa and Wardetsky. Perfect. Yeah, I'm gonna need that. Okay, so this is kind of the whole deal, I believe. I feel like they went really quickly over all of that, which is fine because they're not supposed to teach me how all of these things work. They're supposed to describe their specific thing, but you know, I would appreciate a little bit more hand holding. Okay. Let's write some of these things down because I need to remember all of this. Okay, so that's the Laplacian discretization. So then we got a sum sub j. And then we got the cotangent of alpha sub ij. Plus cotangent of beta sub ij. And then multiply that by u sub j minus u sub I. Yes. Okay. And then I'll remove my notes. Okay. So a sub I. A sub I is the 1/3 of the area of all triangles incident on vertex I. Okay. I'm just gonna say vertex sub I. There you go. I'm making up my own notation. Okay. That one makes sense to me. I'm a little curious if it's if it's supposed to be the area of all triangles or if it's supposed to be the area of all faces connected to VI. Because in my case, those two would be two separate things. I'm going to assume that it's going to be fine if I always interpret it as the triangle area, and I actually get the triangle area even if it's an n-gon. So I kind of like grab the triangle part of that. Unless you have like super non-planar n-gons, but you shouldn't have that anyway. If you have that in your mesh, that's a you problem, you know? That's not my problem. Okay. Can't you just triangulate the n-gon? It would be equivalent. Like triangulating it would be kind of just adding more work and modification to the data when I don't really have to. I could just like get the face normal, assuming it's triangulated around that vertex. But I could do it. Yeah, I could triangulate it. But ideally, it would be nice to not have to like change the topology of the whole thing just for this operation. Okay, so we can express this operation via matrix L. So L equals area. Sorry, I can't see my keyboard. There's a cat in my lap right now. Okay, L sub C. Okay, so Right. Okay. So A is a diagonal matrix containing all vertex areas. Okay, A sub I is 1/3 of the area of all triangles connected to some vertex V sub I. And diagonal matrix is when you only have values in the diagonal, right? In which the entries outside the main diagonal are all 0. Okay, cool. In programming, we call that just a goddamn array of values. Why are you growing out this big box? You're just doing that because you want some kind of operation defined mathematically. Because you have a linear system solver and that's the only format it accepts. Okay. And LC. So what is LC? Is LC a diagonal matrix? Or LC is the cotan operator representing the remaining sum. I have no idea what that means here. I don't know what the cotan operator is, and I don't know what remaining sum. Like the remaining sum of what? Where? Okay, so I guess LC is the cotan operator, question mark, representing the remaining sum. Okay. Heat flow can then be computed by solving the symmetric positive definite system. Okay, so we've got A minus T times the mystery matrix, the cotan operator, I guess, times U equals the what is now the Kronecker delta. So that's delta sub gamma. The mass matrix A. Okay, now they're using terminology. Okay. A is the mass matrix. Okay. Okay, so what are they saying here? They're saying heat flow can be computed by solving this. I thought heat flow was the rate of change of temperature, not the temperature itself. But this looks like you're solving for the temperature itself, not its derivative. But maybe heat flow. I'm guessing this is just solving for you, right? If this is like a linear solve type of situation. we're just solving for u, right? Okay. Is that correct? Are we solving for u here? Okay, I'm just gonna write these down, and then I can reason about the whole thing. We're solving for u. Okay. It is kind of confusing the way that these are set up, because I want u to be on one side of the equation when solving for u. But it never is in these like linear system solver setups. Like I feel like I always need a thing that's like this solves for u. By the way, it does not solve for like the Kronecker delta of gamma, right? This is the note for sleepy me, which is me right now. Okay. So then we got the gradient in a given triangle, right? So here we've got nabla of u, nablau equals 1 over 2 AF. AF is just face area. Presumably. Because there might be some caveats here around non-triangular faces. You know what? Non-simplicial. That sounds fancier. You know? It's also less descriptive. I guess it's just non-triangular faces. There we go. That's better language. Oh. Okay. So this is a sum over I, and we've got u sub I multiplied by the wait. Is this a typo? Did I find a mistake? I feel like ni, shouldn't this be n sub f? And then it should say n sub f here as well? Technically? Because n sub I definitely not supposed to do that in this loop. Because if we get the area of a face, I feel like the face normal should also be sub f. Probably not a mistake, but it is a little bit ambiguous. I don't know. I'm gonna do n sub f. That feels better to me. And then tomorrow when I read this, I'm gonna realize that I was completely wrong and there's a reason why it was written the way it was, but we'll see. Okay, and then we have e sub I. Okay. This needs some explanation. So u sub I is the heat flow at vertex I, and then n sub f is the face normal, and e sub I is the opposing edge vector. This is going to be weird if it's not a triangle, because this scheme doesn't really generalize. Because if this is a quad, there's no natural opposing edge vector. But you know what? I think what you could do, I think you can just pick the adjacent one because you're going in a loop anyway. I wonder if picking the opposing one is just because it's convenient for triangles. But for n-gons, I would guess that just picking like the adjacent one and then going around would be fine as well. I could be wrong, but we shall see. So this is a gradient of I don't know, yeah, gradient of a triangle. That's fine. The a sub f is out of loop though. Yeah. Well, that's fine, right? Okay. Cool. Integrated divergence. Why do I feel like I have one too many line breaks here. Doesn't look good. So this is the integrated. Oh wait, did you mean like the indentation was out of whack? In which case, yes. It wouldn't make sense to index n with I. I didn't do that though, right? Oh, someone in chat was asking. Sorry, I'm stupid. I should really go to bed soon. I am noticing my brain has been deteriorating for a bit. I just want to write down these equations. Because I think a lot of the rest of this paper is going to be irrelevant because it goes over non-triangle meshes. So I think we can finish the paper today. And then maybe tomorrow I'll start maybe doing the implementation for this, which would be fun. But okay, integrated divergence. Divergence. So here, at vertex I. All right, so here we've got can I just write some dollar signs, please? Thank you. Right. Okay. Nabla. Dot. Cot? No. Dot. No. C dot. X equals 1/2 sum iterating or enumerating j. So j is every triangle connected to the vertex. Or like it's the index of every connected triangle. Okay. So we are summing over every connected triangle. And then we are getting, let's see, we're doing the let's see, the cotangent of, oh god, this is throwing me off. Because I always use parentheses for trig functions, and it's throwing me off that there are no parentheses around this angle. But that's fine, I guess. I'm guessing it's just a cotangent of this angle, and then it's multiplied by this. I'm guessing. Okay, so we got the cotangent of theta 1. And then multiplied by the dot product. Is that the dot product? You never know with all of these Riemannian metrics and inner products. It's in this area, you know? So E sub I dot X sub J with a vector X sub J. What is X sub J? Oh wait, that's a normalized vector field. Oh yeah, that's just the normalized version of this. That's X. Okay. So that's basically the step after this. X is then the normalized vector field. Okay. So let's see. Plus the cotangent of theta 2. Oh wait, it's supposed to be E sub 1 and E sub 2. Okay. And then dot X sub J on both. Okay. Okay. Valid. We have some kind of equation. Okay. How do I describe this? So E1 is the I take a screenshot and then I paste it. That's how I explain this. Beautiful. Oh, here we go. Can I move this someplace that doesn't hurt my eyes? Okay, you know what? No. Nope, stop. Hello? Can I delete stuff? Okay, there we go. Ugh, that feels much better now. I'm feeling a little bit more okay. What's with this alignment? Oh my. Okay. I will clean this up tomorrow. Okay. Okay, so J is iterating all over all of the incident triangles containing vertex I. Got the opposing angles. If we let B be basically just a scalar value associated with each vertex, so when they say be the vector, they mean array. So be the array of integrated divergences of the normalized vector field X. And the final distance functions is computed by solving the symmetric Poisson problem. Okay. Wait, are we solving for B or phi here? Because I thought, wait, is B known? Let B be the vector of integrated. Oh wait, this is the integrated divergence. I thought this was just the divergence, not the integral of the divergence. Where's the integration symbol? How does that work? Okay. So is this just yeah, I guess B is like doing this per face. Right. Okay. So we're basically saying let B hold all the integrated at each vertex. Wait, does someone write something that I missed? Oh, I had it set to top chat. I might have missed some messages. YouTube likes to always default to top chat instead of live chat everywhere, so I have to manually set it up every single time to not be top chat. Okay, where is the thing? So we have L sub C L sub C times phi equals B, which is what? This is the final distance function. The final distance function is computed by solving the Poisson equation. Oh, there was a qualifier there. Symmetric. Poisson equation. Okay. Okay. Theoretically, this should be all we need. Plus a linear solver. It's just like a tiny extra little device on the side, but okay. All right. Before I go to bed, I'm going to make a small change. So let's see, what colors do I want for this? What do I usually use for distances? I don't think I have a color that I usually associate with distance. I'll just use my brand colors for all of these. Wait, I think I can just, yeah, okay. There we go. Conten? Coten? Okay. There's not enough colors. Something's not right. We need to color more things. An F? Do I have a color for the flat tangent space normal? I thought I did. No. Okay. It's over. Oh no, you know what? We're gonna do the z-axis color. That's where we're going to give the face normals. Where's... There we go. Okay. I'm failing my goal of making things more clear using colors because everything's so separate. LC. I think LC deserves its own color. It feels green to me. I don't know why, but it's just giving green, you know? Okay, is there any other? No? Those. Oh, good job. Great. There we go. Okay. Wow. U probably deserves a color. U represents the heat. And that kind of feels like it should have like a warm color, like an orange or something. That makes sense to me, I think. God damn it. This is important, okay? I need to aesthetically appreciate my math. Otherwise, I won't actually appreciate it. This equation is bleak. There's no color in this one. Wait, there was another LC that I didn't color it. It's over. Sorry? Mr. Cat, why are you poking my monitor? What did my monitor do to deserve that? Mr. Buddy? Oh, okay. Okay. Finally, maybe the mass matrix should also have a color. What color are we doing here? Mass feels heavy. But my blue is a little bit too light cyan. I don't know. I don't know if my brand blue is gonna work here. I feel like it's gonna give the wrong vibes. It feels too light. If anything, my red feels heavier than the blue. But that's okay. We're just gonna accept that. Still no color in this one. Okay. Okay. Oh, that's an I. Or that's an A. There we go. feel like we should just give a color to X as well. It's like the last thing that should probably have a color. So what do we got left? We're using red, green, blue, yellow, orange. We don't have anything purple. I mean, I am sort of using the Z color for phase normals. So the normalized vector field is kind of like one of the tangent directions. So I think I'm gonna do the x-axis color for that. I'm hoping it's not gonna like conflict too much with the distance color because those don't really go together. But hopefully they're not gonna be too adjacent. Mm, mm, mm. That's an A. I missed the A. Did you define those colors in some sort of library? You can define colors in LaTeX, and I'm using like global. You can define like global functions. So I have a bunch of global functions that are applied to every document, which requires a plugin to have. I think it's called something with preamble. It's like a preamble that's like attached to every note. So I have a preamble where I define LaTeX globals. Okay. No, shit. Wait. How many? Oh, hold on. That was the wrong one. That one's fine. This one was not fine. Cool. Then I think we've only got. Is there anything? I guess I could color the L, but it doesn't really matter. Extended math jacks? I don't think so. I forget. But I don't recognize that. Okay. I think that's going to be about as far as we get today. I'm just going to read a little bit more, just see if we're about done, which I think we are. Okay, so this should solve, and we should get our distance. It generalizes to higher dimensions, blah, blah, blah. Polygonal surfaces. For a mesh with not necessarily planar polygonal faces, we will use the polygonal Laplacian defined by Alexa Wardetsky. The only difference in this setting is that the gradient of the heat kernel is expressed as a discrete one form associated with half edges. Okay, so the gradient of the heat kernel. So that's this thing. That is the thing that I was directly pointing out will like as a thing that requires something else. That's validating. I noticed that at least. Is expressed as a discrete one form associated with half edges. Hence, we cannot directly evaluate the magnitude of the gradient needed for the normalization step. To resolve this issue, we assume that the gradient of u is constant over each face, implying that the integral over Jesus Christ that the where UF is the vector of heat values in the face F, AF is the magnitude of the area vector, and LF is the local weak Laplacian. We can therefore approximate the magnitude of the gradient as the square root of all of this. This quantity is used to normalize the one-form values associated with half edges in the corresponding face. The integrated divergence is then given by dTm alpha, where alpha is the normalized gradient. D is the co-boundary operator, and M is the mass matrix for one-forms. C, a different paper for details. Oh boy, okay. These operators are applied in steps 1 to 3 as usual. Figure 7 demonstrates distance computed on an irregular polygonal mesh. That's this one. Wow. Wow. Kitten mesh. True. Okay, point clouds. Don't care. Super don't care. Choice of time step. I remember something about this where the time step should be something related to the mean length of edges or something that converges. Smooth distance, I am curious about. Okay, so we do have a few more things that I can read tomorrow or whenever I continue with this. It is also possible that my voice is going to be completely gone tomorrow. So if that's the case, then I'm not going to be able to stream. So I can tell that my throat is unhappy right now. Probably should have stopped streaming earlier, but too late. Too late. We learned a bunch about the heat method. Still having throat issues? Yes. Which is kind of concerning. Yeah, it's not supposed to last for over like a week. It's supposed to go away and not persist after a month and a half. So I'm probably gonna see if I can book a time with a GP and see if I can get some answers as for who did this to my throat. Then it's probably me, but if there's a way to fix it, or if I have permanently damaged my larynx, who knows? Maybe that's what happened. I hope not. But yeah. I think this was productive at least. Any questions or thoughts before I head off? This shirt does not work on camera. This shirt is just like deleting every photon that touches it, so it's just creating a void. I feel like I look like Thor, where like everything just absorbs. Was that paper written by Keenan Crane? Yes, he's one of the authors. I will send you the paper. There you go. Here's the paper for those of you who are curious. Does it really need to be so crazy, like the solution to this? Or do cat trees cause cats, or is it the other way around? I think it depends on if it's a closed or open system. If it's an open system, then cat trees absolutely cause cats. But in a closed system like my home, I think it's the cats that cause the cat trees, I think, on average. So if your question was like, does it have to be this complicated to implement the heat method or to implement the geodesic distance? In a way, like it's like yes and no. If I want geodesic distance, there are ways of calculating it that is easier than to go through this entire paper. It's just that it's going to be too slow. It's going to be oh my god, yeah, I can feel my throat is giving out. There are easier ways of doing this. but they're going to be too slow. The really cool thing about this algorithm is that it's parallelizable, so I can do it on the GPU, and it can do these things with a lot of elements, because my meshes are gonna potentially be pretty dense. There's gonna be thousands of vertices, not like 5, you know? And so I need to be able to compute this whole thing really efficiently. This is a questionable set of vertices over here. Maybe this is not the best geometry. I feel like I kind of messed up this. What would have been a beautiful torus. There we go. Oh yeah, look at this. Look, check this out. I have... Oh wait, I'm not showing my screen. Oh my god, I'm sorry. Zoop. Check this out. Look at this. I have half edges. I have half edge selection in my 3D modeling tool. This could only be done by someone who's very nerdy about this. Not a single artist in the history of 3D modeling tools have asked for a half edge selection tool. But you know what? I'm gonna be the change I want to see in the world, and I'm gonna normalize half edge selection in modeling tools. This is gonna... What's the marketing spiel? It's like, this will revolutionize how artists create and find new frontiers in 3D modeling never seen before. So, something along those lines. Is it too late to ask what a half edge is? It's really an edge that belongs to a face. So if there's multiple faces around an edge, there's going to be one half edge per face. And it's called half edge because usually you only have up to 2 faces meeting at an edge. And so 2 half edges kind of forms a single edge, right? And half edges have a direction, unlike edges. And so half edges kind of contain orientation information in a way that edges don't, which is like extremely fundamental. Extremely fundamental to mesh operations, but for some reason it's never exposed to users. And I think that is a mistake. I think there's a lot of cool things you might be able to do if you have the design space of letting users select half edges, because you can kind of resolve all of the potential ambiguities that you have with edges. Because like with edge loops or edges, there's no way for me to make a decision about, like, if I want to cut this edge loop open and then I want to move one of the sides, there was no way for me to select which side I wanted to move, right? But if I were to cut with half edges, then I could disambiguate that, right? Like if I selected a half edge loop, like this, if this was my selection, there is a way to distinguish this from this, right? Oh, wrong operation. Which does let you disambiguate those things. I think that's kind of cool. These half edges can be added and subtracted like vectors, multivectors, right? No. Half edges are topological. They're not geometric. But you could like, I mean, each half edge can be converted to the vector along that edge. Half edges also have this additional aspect to them where half edges not only contain data about this edge as it belongs to the face, but also this vertex as it belongs to the face. So it's kind of a combination of per face, vertex, and edge data in one single data structure. So if there's stuff like vertex normals also live inside of half edges rather than vertices, because vertices are shared by all of these faces, but vertex normals have to be per face. So per face vertex normals would live in these 4 half edges. So that's why there's kind of a dot at the root of each of these half edges, because it also represents the data at that dot. But yeah, okay, my throat is actually starting to hurt quite a lot, so I should really not push it. But thank you so much for joining. I hope this was interesting or entertaining or otherwise helping you get by in your day, whatever it was you were doing. Luckily, I don't think this stream was interesting enough to distract you from something that you were supposed to do. So that's good. Do you have clockwise faces? I am using a left-handed coordinate system, so I have a left-handed winding order for my face normals, if that's what you're asking. Does it let you reverse half edges? Yes. I can just show you. There you go. I have reversed the half edges. This is what flipping a face normal is equivalent to reversing half edges, because half edges define the face normals. Okay. All right. Toast is yelling at me. I think he wants something. He probably wants me to go to bed. And so does my throat. Thank you all so much for joining. Thanks for showing your progress. Half edge is going to be so cool. I hope so. It is. I think it's cool. I think it's exciting. If you want to support the stuff that I do, then I have a Patreon. So feel free to go there. If you happen to sit on an enormous pile of money and you just want to like throw it in my direction, or if you're sitting on a very small amount, that's also really appreciated. Yeah, it's probably the easiest way to support the stuff that I do. And feed my cats. Trying to think if there's anything else I wanted to mention. Oh yeah, the VOD is going to be on YouTube. So if there's stuff that you missed or you wanted to rewind, it's going to be on YouTube. It's going to be under the live tab. Yeah. Why not collaborate with people online? Because I am very unpredictable and I'm terrified of commitment, and it's scary if people depend on me for literally anything. And I like doing things on my own. That's the honest answer. All right. Okay. I don't think there's anything else I want to say. Actually, I want to show Toast because he was yelling. You need to see Toast. That's going to be the last thing before we. Hello. This is my little boy Toast. He is not 17 years old. I believe he's 4 years old. He's not very old. He don. I don't think he wants to be here. Yeah. Yeah, you want to run around and yell. Because I am not going to bed. Yeah. Will you support some node-based workflow? Not for 1.0. No. Okay. Thanks for joining, everybody. This was fun. Rip my voice. I don't think I'm going to be able to stream tomorrow. If I will, if I do stream tomorrow, I'm almost certainly not going to be able to talk. Unless it's miraculously amazing tomorrow, but probably not. But yeah, right. I'll probably do another session, yeah. What I'm probably going to do is tomorrow I'm probably going to clean up my notes. I mean, unless I cheat and I'm like, you know what? I want to do this off stream and then I just do the rest off stream. But I presume some of you would like to see the implementation as well. Yeah, I'll try to do it. I'll try to do that. But probably not tomorrow in that case, but maybe. But yeah, thanks for joining, everybody. It was fun. I will see you all next time.